What was the universe like during its long, dark ages before stars? How did gravity and dark matter shape the first stars and galaxies? Why do cold molecular clouds serve as cradles for newborn stars? In the beginning, there was darkness, a profound and endless night draped across the young cosmos, for no stars yet shone to break its velvet darkness. The universe had been born in fire and light, but now it had cooled and dimmed, leaving only a faint glow from creation's afterglow, and the rest was silence. This hydrogen, along with a touch of helium, was forged in the universe's fiery birth and has drifted ever since, cooling and waiting in the dark. It was a night of hydrogen, a time when the vast ocean of space was filled only with the simplest of elements, hydrogen and a whisper of helium, spread thinly like a cosmic mist. In this primordial quiet, space was not truly empty, but filled with this ghostly gas. The hydrogen atoms drifted for millions upon millions of years, meeting and parting in the dark void. Without light, the cosmos seemed asleep, wrapped in a cold slumber. Yet something subtle was at work, even in that stillness. Through the darkness moved an invisible force, gravity, gentle and patient, tugging ever so softly on the scattered atoms. Gravity's pull was weak at first, its effect almost imperceptible. But over vast expanses of time, the slightest densifications began to grow. Where a few more atoms happened to gather, their combined mass tugged on others. Slowly, quietly, the diffuse hydrogen mist started to pool into delicate streams and clouds. It was as if gravity were whispering a lullaby to the drifting gas, coaxing it into a closer embrace. As eons passed, those whispers grew into a quiet urgency. The temperature of the universe had fallen low. In these deep cosmic nights, the hydrogen gas was cool enough to drift without much agitation. In places, what once was an almost uniform haze began to show slight variations, tiny seeds of what would become clouds. These were the first hints of structure in the darkness, the earliest shadows of what one day might become stars and galaxies. But for now, they were just faint smudges in an otherwise black sky, invisible except to the persistent pull of gravity itself. It's remarkable how such darkness can hide so much potential. Entire stellar nurseries concealed in plain sight, waiting for the moment to reveal their treasures. Imagine floating through this silent expanse. There are no points of light around you, no stars to navigate by, only an all-encompassing darkness and an almost unnoticeable thinning or thickening of the blackness where the hydrogen is a bit denser. Far, far in the distance, a dim afterglow of the Big Bang still faintly illuminates the void, but it is not bright enough to chase away the darkness, only enough to paint it with the slightest ghostly glow. This afterglow, the cosmic microwave background, is like the memory of a sunrise long past, now cooled and stretched so thin that it provides no real light, only the barest whisper of warmth. In this darkness, if you could somehow see the invisible, you might notice that here and there, the blackness is just a touch deeper. Those are the gathering clouds, where gravity is drawing the hydrogen into denser patches. These patches are vast and diffuse, many light years across, but compared to the emptiness around them, they are the beginnings of something new. Over time, these clouds become the cradles of the first stars. But before any star ignites, the darkness reigns supreme for what feels like an eternity. Long before the first star, An invisible framework was already in place. Wisps of dark matter, shaping space with their gravity, had formed a faint cosmic web across the universe. Hydrogen collected along this web's filaments, like morning dew coalescing on a spider's thread. At certain crossroads in the web, larger pools of gas began to accumulate, the future sites where the very first galaxies and stars would ignite. This gossamer network was imperceptible to any eye, yet it quietly orchestrated the movements of gas that would lead to the dawn of starlight. The hydrogen clouds continue to coalesce under gravity's patient guidance. The process is slow and delicate. Each region of slightly higher density pulls in more gas from its surroundings, growing a little more massive and drawing in even more. It's a gentle amplification, gravity taking advantage of any chance gathering to strengthen its hold. And as these clouds grow denser in their centers, a quiet transformation starts. The gas in those cores begins to warm from the pressure of its own weight. But at this early stage, even that warming is faint. The cosmos still appears unchanged to any hypothetical observer drifting in the void. There is no visible sign yet that deep within some of these unseen clouds, the first sparks of starlight are preparing to ignite. All remains calm, cold, and profoundly dark. It is a silence unlike any other, a deep hush that feels eternal, yet is full of latent promise. Yet within those cool, silent clouds of hydrogen, destiny is taking shape. The universe is holding its breath, as if in anticipation, poised on the brink of illumination. Then, finally, after patience beyond imagining, the dark yields to something new. In one of these dense knots, in a quiet corner of the cosmos, where enough gas has gathered, the first true star ignites. It happens quietly, at first. No dramatic burst, just a soft and steady shine, kindling where there was none before. In that moment, the cosmic night is broken by a newborn starlight. A pinpoint of brilliance flares into being where there was absolute dark. And then another, and another, as if the universe were slowly lighting candles after a long night. These first stars are unlike those that will follow. They are massive and bright and short-lived, forged from pure primordial hydrogen and helium. But their birth marks the end of the universe's dark ages. The gentle glow of these new stars spreads across space, heralding the first morning in a universe that has known only night. Their brilliant rays reach into the surrounding emptiness, awakening the gas around them. The once invisible hydrogen now begins to glow in response, as starlight energizes it and lifts the veil of the cosmic night. The era of darkness ends as these pioneers blaze out, marking the universe's transition from shadow to light. The silence of the cosmic night is gone, replaced by the faint, beautiful radiance of young stars. Though they are few and far between at first, their light travels far, seeping into the darkness and giving it color. The universe, once a sleeping infant wrapped in darkness, has opened its eyes, and the gentle glow of those eyes, the stars, will watch over the cosmos for eons to come. It's wondrous to contemplate. Out of the vast emptiness and silence, light has been born. From an endless night, the cosmos has lit its first candles. Over the next hundreds of millions of years, the light of those early stars and the galaxies they gathered into transformed the universe. The cold hydrogen fog that once filled space was heated and cleared, and the cosmos, now illuminated by countless stars, would never return to the pure darkness from which it came. Long after the first stars brought an end to the primal darkness, the universe continued its cycle of creation. In galaxies that formed later, including our own Milky Way, the birth of stars carried on in secret, secluded within vast clouds of gas and dust. These are the molecular clouds, enormous, cold assemblies drifting through the galactic spirals like dark, silent islands in a sea of starlight. From afar, they appear as bottomless shadows against the glittering backdrop of stars, patches where the starlight beyond is extinguished by a thick veil of dust. They are truly cradles in the dark, cosmic nurseries where new stars are conceived away from any prying light. They can be truly immense, some stretching across dozens of light years and weighing as much as 1,000,000 suns. In their cold embrace lies material enough to give birth to not just one star, but entire clusters of stars. From our vantage on Earth, some of these dark clouds show themselves only as mysterious silhouettes. There is the Horsehead Nebula, for instance, appearing like the profile of a horse's head against a faint, luminous glow. And the Coal Sack, a great black patch in the Milky Way where no stars shine through, as if a piece of the night is even darker than the rest. These shapes are not empty voids at all, but full of hidden matter. To the eye they look like holes in the heavens, but in truth they are immense clouds, heavy with gas and dust, and the promise of new stars. Inside a molecular cloud, the environment is calm and hushed. The gas here is mostly hydrogen, but in a different form than in the early universe. It has paired into molecules, 2 atoms bonded together. The temperatures are incredibly low, just a few tens of degrees above absolute zero. In this deep cold, atoms move lethargically, and the gas can settle into dense pockets without being blown apart by thermal energy. Mixed in with the gas are tiny motes of dust, microscopic particles of silicates, carbon, and ice, little specks that are remnants of earlier stars. Together, the gas and dust weave a dark tapestry that both nourishes and conceals the embryonic stars forming within. Imagine yourself drifting into one of these clouds. At first, it's nearly pitch black. The dust particles block out the light from outside, creating a sanctuary of darkness. As you glide further in, you might notice a very faint glow in some places, perhaps the subtle infrared warmth of the cloud itself. But mostly, it's an abyss of shadow. Yet this darkness is comforting, protective. It shields the fragile process taking place inside from the harsh radiation of nearby stars. Here, in this secret night, gravity is once again at work, gently gathering clumps of gas together, just as it did in the primordial cosmos. Within the cloud, there are regions where the material is a bit denser. These are the cloud cores, the seeds of future stars. Each core might be only a small fraction of the cloud's size, but even a small fraction of a giant cloud can hold many times the mass of our sun. These cores are so well insulated by their surroundings that little of their heat escapes. As gas continues to pile in, the cores grow colder on the outside, but denser and slightly warmer on the inside. Pressure begins to build in the heart of each core, a silent sign that a transformation is underway. Unseen and silent, a new phase in the star's birth is underway in one of these cores. The dark cradle has done its job of gathering and protecting the nascent star up to this moment. Now, as the core condenses further, a protostar is taking shape deep inside the cloud, still hidden from view, but growing in strength. The cloud around it still looks impenetrably dark from outside, but deep within, the promise of light is growing. Soon, this cocoon of gas and dust will hold a newborn star, its faint glow still wrapped in shadow. Often, these stellar nurseries are not lonely places. Many cores can form within a single cloud, giving rise to a whole cluster of stars that will be born together. In the dense heart of the Orion Nebula, for instance, thousands of stars are forming in a single sprawling complex of gas and dust. Yet from outside, parts of that region appear simply as obscuring bands across the sky, dark nebulae silhouetted against the brighter backdrop of the Milky Way. Only when those stars eventually light up and push away the surrounding gas will the nursery unveil its treasure. For now, everything inside remains in darkness and quiet. Deep within, molecules collide gently, dust grains drift and sometimes stick together, and chemistry slowly unfolds. Traces of more complex molecules form in these conditions, simple ices and organic compounds painting the dust grains. These chemical traces are like whispers of future possibilities, including ingredients for planets and life that will come much later. But in this moment, they simply accumulate in the cold, dense pockets, while gravity continues its patient work on the gas around them. It's remarkable to think that within such darkness and stillness, so much is happening on a microscopic level. In these preparations, the dark cloud has quietly laid out everything needed for the coming of the light. The stage is set, and the long night inside the cloud will soon give way to the gentle dawn of a new star. In the lightless interiors of these cosmic nurseries, another quiet process is underway. Scattered among the hydrogen gas are those tiny grains of interstellar dust, so small that millions of them could dance on the head of a pin. These dust grains are the ashes of previous generations of stars. Little bits of carbon, silicon, and other elements forged in ancient supernovae. Now they drift in the cold, molecular cloud like motes in a dark room, and on their surfaces a slow and delicate chemistry takes place. The dust grains are cool and welcoming, and they tend to collect thin layers of ice. In the frigid darkness, atoms and simple molecules that land on a grain can stick to it and remain. Over time, these accumulations grow into icy mantles encasing the grains. Within these frosty coatings, atoms meet and bond in ways they rarely could in the emptiness of space. A hydrogen atom finds another and forms H2, the simple molecule of two hydrogen atoms, which is more stable than the atoms drifting alone. Nearby, an oxygen atom might join with two hydrogens to form water, which immediately freezes onto the grain as a tiny crystal of ice. Carbon and oxygen might form carbon monoxide. Methane, ammonia, methanol. Many simple compounds take shape in this quiet chemistry, each molecule becoming trapped on a dust grain surface as part of the icy mantle. Even modest organic molecules can arise. Astronomers have detected hints of simple sugars and other prebiotic compounds forming in these cosmic laboratories, sowing seeds for the ingredients of life. This process happens at an incredibly slow pace. A single dust grain in the deep interior of a cloud might wait centuries just to accumulate a thin layer of molecules. But time is abundant in these quiet clouds. Over thousands and then millions of years, the chemical inventory grows richer and more varied. These tiny, icy grains are like treasure chests containing the seeds of future complexity. Indeed, If one could hold a handful of this cosmic dust, it would seem like nothing more than a pinch of fine, dark powder. Yet hidden in that pinch are the makings of so much: water for future oceans, carbon for future life, locked in miniature crystals and fragile molecules. It's as though the ingredients for worlds and living beings are being quietly stockpiled in the most unassuming places, waiting for the right moment to be used. In this deep cold, nature performs a delicate form of alchemy, forging water, organic molecules, and other treasures invisibly on dust grains. It's a quiet artistry, crafting the building blocks of everything to come in utter secrecy. Over countless years, the dust grains' icy mantles become rich with simple chemicals. Water ice, a bit of formaldehyde, a hint of methanol, even simple sugars or molecules that hint at the building blocks of life can form in these frozen films. The quiet accumulation on these dust motes is laying down a chemical foundation for the future. In their molecular ices lie water and organic ingredients that one day could become part of comets, oceans, or even living cells on newborn planets. For now, they are just inert substances, unassuming and inert, kept in the dark until destiny calls them elsewhere. While the dust grains are busy gathering ices, they also play another crucial role. They help the cloud to cool. When gas atoms collide, or when a region begins to collapse under gravity, it generates a bit of heat. Dust grains, coated in their ices, can absorb some of that heat and then re-radiate it away as faint infrared light. The cloud emits a soft glow in wavelengths our eyes cannot see, shedding energy quietly into space. This cooling is essential. It allows the cloud to condense further without building up internal pressure that would stop the collapse. In this way, dust and ice act as gentle regulators of star birth, making sure conditions stay just right for gravity to keep drawing the cloud inward. Imagine drifting deeper into the cloud's core with this knowledge. All around, invisible to your eyes, countless tiny grains float alongside you. Each one is a micro-world, its surface hosting a thin film of water ice peppered with other simple molecules. In the darkness, you cannot see them, but if you could shrink down to their scale, you would witness a beautiful ballet of chemistry. An atom lands and sticks, jiggles in place with a bit of energy, then meets another atom that has also settled nearby. They join, releasing a faint bit of energy that the grain carries away, and a new molecule is born. It is a quiet, almost ghostly dance, taking place on uncountable millions of dust grains throughout the cloud. Sometimes, a passing cosmic ray or a stray glimmer of ultraviolet light from a distant star might penetrate the cloud's outskirts and strike a dust grain, triggering a tiny reaction and spurring a bit of complexity in the chemistry. But mostly, it is dark and still, and the transformations are unhurried. Simple though these molecules are, they are the precursors to so much. Already, the cloud's makeup is more than just hydrogen and helium. It has a dash of everything that came before, all the elements that earlier stars forged and then cast into space. That stardust, now cooled and repurposed, mixes with primordial gas to create a richer environment for the new stars soon to emerge. For now, we remain in the moment before that release. All through the cloud, dust and ice quietly do their work, shaping the conditions of star birth in seen and unseen ways. They dim the light from outside. They cool the cloud from within, and they assemble ingredients that make each newborn star's environment uniquely rich. In this patient, invisible alchemy, the futures of worlds are being seeded even before the star that will illuminate them has been born. And as the core of the cloud continues its slow collapse, this accumulation of dust, ice, and molecules has prepared the way for the next stage of the star's journey from darkness into light. The stage is set. In these preparations, the dark cloud has provided everything needed for the coming of the light. The long night inside the cloud will soon give way to the gentle dawn of a new star. Not all is tranquil in the birth cloud. Even as gravity pulls inward, the gas within the molecular cloud moves in subtle, restless ways. Turbulence, random, chaotic motions of the gas stirs the cloud like a slow, sweeping breath. These internal motions create irregular densities, long, thread-like filaments and fluffy clumps that snake through the darkness. If you could see these filaments, they might look like faintly glowing spiderwebs stretched over light years, threads of gas and dust where material has been swept and compressed by turbulence. Along these wispy threads, there are junctions and knots, points where multiple filaments intersect or where gas has piled up a little more. These knots are seeds of potential stars, just waiting for a final push to collapse under their own weight. In this intricate web, a gentle tug of war is playing out. Gravity is always pulling the gas inward, trying to gather the filaments and knots into even denser clumps. But opposing gravity are the forces of pressure and motion. The gas in the cloud, cold as it is, still has some pressure that resists being squeezed. Turbulence itself provides support in a way, as the gas motions push outward or swirl around, counteracting collapse in some regions. And woven through the cloud are magnetic fields, invisible strands of force that thread through the gas. They too hold the gas back slightly, like delicate cords wrapped around the cloud's fragments, adding a bit of stiffness to an otherwise yielding medium. All these effects, pressure, turbulence, magnetic tension, act like a gentle hand against gravity's persistent pull. For a time, this stalemate can maintain itself. The filaments undulate softly, their shapes shifting under the slow-changing flows. Some knots that had started to condense might disperse again if local turbulence buffets them too strongly, sending their gathered gas back into the surroundings. Other regions might find a delicate balance where gravity and pressure nearly cancel out. In such a calm state, a cloud can exist for millions of years without forming a star, content to simply drift as a dark nebula across the galaxy, its potential for creation held quietly in check. In some ways, one might imagine an analogy to clouds in our own sky. On a warm summer day, parts of a cloud might grow dark and heavy with the promise of rain, while other parts are held aloft by gentle updrafts, delaying the shower. In the molecular cloud, gravity is like the cool weight making pockets ready to rain down into stars, whereas turbulence and magnetic whispers are like subtle breezes holding portions of the cloud up. It's a delicate balancing act on a cosmic scale. Yet, bit by bit, gravity tends to win in certain favoured places. The densest parts of filaments, especially where several filaments meet, gather more mass and begin to slow the internal motions. There, the gas becomes more tranquil, losing some of its turbulent support. A knot deep within a filament might begin to feel gravity taking over as the dominant force. When that happens, the tug of war shifts decisively. The gas in that core starts to give way, and collapse resumes with greater purpose. Surrounding material starts streaming down the filament, feeding the growing clump. The filament itself may begin to fragment, each segment falling into its own dense knots like beads on a string, each bead destined to become a star. We can find scenes like this throughout the cosmos. In the Eagle Nebula, for instance, a cluster of bright young stars is illuminating and eroding a nearby cloud. Their light has sculpted the gas into towering columns known as the pillars of creation. Within those dark pillars, like stalagmites in a celestial cave, new stars are forming, hidden deep inside. Jets from those newborn stars have been observed streaming out of the pillars' tips, even as the pillars themselves slowly crumble under the assault of intense starlight. It's a dramatic example of the cycle at work, the energy of existing stars triggering new stars to form, while simultaneously dispersing the very clouds that nurture them. Sometimes the balance can be tipped by a gentle nudge from outside. The distant echo of a star's death, for instance, a ripple from an ancient supernova explosion, might sweep through the cloud and momentarily compress part of it. Or perhaps a slow collision, or brushing encounter with another cloud, sends a wave through the gas. These subtle pushes can trigger a collapse in regions that were teetering on the edge, giving gravity the upper hand for a moment. In this way, one star's end can sow the seeds of new beginnings, linking death and birth in the cosmic cycle. Picture yourself in the midst of this process. You float alongside a long, tenuous filament of gas that winds through the darkness. It is silent, yet gently moving. Currents of turbulence sway the filament back and forth. Ahead of you, two such filaments converge, and at their intersection, a roundish cloud core has formed, darker and denser than the space around it. For a while, it trembles, but holds its shape against the internal stirrings. But slowly you notice streams of gas trickling along the filament toward that core, as if drawn by an unseen promise. The core is starting to gain mass, and its gravitational pull grows stronger. Turbulence that once propped it up is calming here, unable to prevent the inevitable any longer. The collapse of this core is not an explosive event. It is more like a slow sigh. Over tens of thousands of years, the core shrinks and grows denser. Its central parts heat up as gas falls inward, converting gravitational energy into warmth. If you could listen somehow, you might imagine a soft creaking as the material settles, the quiet groan of a structure giving in to a heavy load. But all is truly silent in space, and the collapse continues in serene quietude. Finally, in one small corner of this turbulent web, gravity's perseverance pays off. The gentle tug of war resolves, and the miracle of star birth enters its final act. A new light is about to be born. Importantly, not every part of the cloud collapses at once. While one core gives birth to a star, another nearby may still be in stasis, held up by the whims of turbulence or a reinforcing twist of magnetic field. In this way, a single molecular cloud can host multiple stages of star formation simultaneously. Some newborn stars already igniting in one region, while elsewhere, gas is only just beginning to gather its courage to collapse. The result is a patchwork of life stages, a tapestry of becoming, all hidden within the same dark cloud. Eventually, gravity's victories add up. The cloud that was once supported and stirred by turbulence begins to quiet down as more and more of its material sinks into stars. The filaments either break apart as they feed the cores, or dissipate as their gas is used up and then blown away by the energies of the newborn stars. What began as a jumbled, turbulent web is gradually giving way to a simpler structure, a collection of newly formed stars swaddled in the remnants of gas and dust. The tug of war has yielded to creation. The moment a star-to-be gains the upper hand over its environment, it moves to the next stage of existence. And as one such core in our imagined cloud finally collapses enough to form a very dense center, we edge ever closer to witnessing the birth of a protostar, the first glimmer of light from what will one day be a new sun. Within one such cloud core, the slow collapse has indeed given rise to a new object. What was once a diffuse clump is now a much denser, hotter center. A protostar, the first embryonic stage of a star's life. It's not yet a true star by the strict definition, for the heat and light it produces come not from sustained fusion, but from the gravitational energy of its own collapse. Still, within that opaque cocoon, something glows. It's as if an ember has been kindled in the heart of the cloud, a warm, dim radiance suffusing the surrounding gas and dust. This is the first light of a forming star, soft and reddish, trapped inside layers of infalling matter. Around the protostar, the collapsing material doesn't all fall straight in. It spirals, forming a disk. Like water circling a drain, gas and dust swirls around the newborn star in a flattened loop. This disk is enormous in extent, stretching for many billions of kilometers around the young star. It holds enough raw material to one day form not just one world, but an entire planetary system. Within it, material gradually drifts inward to feed the growing protostar. But the disk is also a busy place in its own right. It's the birthplace of planets in the far future, but even now it regulates how the star grows. The rotation of the disk and the star's own spin generate magnetic fields that thread through the surrounding space, connecting the star and disk in an intimate dance. As the protostar continues to accrete mass from its disk, it occasionally encounters a problem. The infalling material can't all be smoothly absorbed. The buildup of energy and rotation has to find a release. And so, in a spectacular yet still hidden display, the protostar launches twin jets of gas out from its poles. These jets are narrow, high-speed streams of particles and energy, moving at hundreds of kilometers per second or more, hurtling out in opposite directions along the star's axis of rotation. They carry away excess energy and angular momentum, acting as a relief valve for the forming star. To the protostar itself, this is a stabilizing action, but to the surrounding cloud, it is a momentous announcement. The jets blast through the infalling envelope of gas and dust, carving tunnels through the cocoon that surrounds the protostar. Imagine two beams of faint light, or a powerful wind pushing the dark curtain aside. Each jet travels outward, boring a cavity into the molecular cloud. In time, each jet could extend a great distance, even a light year or more, into space, as it continues to blow outward. In their wake, they leave warmer, cleared channels, like narrow chimneys in the cloud through which light and matter can escape. Along the edges of these cavities, the interaction of the jets with the cloud causes shock waves that make the gas glow faintly. If one could peer with the right kind of sight, one would see these as ghostly, luminous outlines tracing the path of the jets, subtle neon signs that a new star is forming here. Within the quiet of the cloud, these jets are violent in effect, but still silent in sound. They do not explode all at once. Rather, they stream outward continuously over years and centuries. Bit by bit, they blow away the shroud that envelops the protostar. The cavities they open grow wider, and much of the gas and dust that once hid the protostar is eventually expelled back into space. This process both prevents the young star from gathering too much mass too quickly, and ensures that, eventually, the star will emerge from its birth cloud to shine openly. With enough time, a significant portion of the original cloud will be dispersed by these processes, returned to interstellar space. Only a fraction of the gas ultimately becomes part of stars. The rest is blown away, perhaps to gather again elsewhere and try once more to create stars in the distant future. The image of this stage is striking. A dark, cold cloud with a secret warm glow inside, and two faintly illuminated channels tunneling out to space, like a butterfly about to break from its chrysalis. The protostar is still deeply nestled in dust. If you were nearby, you wouldn't see it directly with your eyes, only darkness and subtle hints of motion. But you might notice the outflow if you had infrared vision, lobes of outstreaming gas on opposite sides of an invisible center. These outflows can sometimes be seen as beautiful nebulous structures called Herbig-Haro objects, where the jets collide with the ambient cloud and excite it to shine. It's as if this infant star, not yet visible itself, is using these jets to make its presence known, a cosmic birth announcement in the form of twin beacons. Though a human observer drifting in space would not hear or feel these outbursts, they mark a critical transition. A star is declaring its presence in the only way it can before its light breaks free, by pushing on its surroundings. It's as if the baby star is taking its first breath and crying out, not in sound, but in beams of energy, proclaiming to the cosmos that it has arrived. Gradually, as the protostar accretes more mass, it also stabilizes. The outflows might come in fits and starts. Sometimes they wane. Then a fresh surge of infalling material triggers another burst. Each episode clears a little more of the surrounding envelope. Through the tunnels carved by the jets, the warm glow of the protostar begins to peek out. The darkness of the cloud is no longer absolute. It has cracks and openings now, through which a new light leaks. These first embers of starlight, though faint, signify that the protostar is maturing. It won't be long, astronomically speaking, before the star sheds its cocoon entirely. The jets have done their pioneering work, announcing the coming presence of a star to the universe. In time, the fully formed young star will illuminate the remnants of its birth cloud, turning the lingering dust into a soft blue reflection nebula and causing the gas to glow with pinkish-red hydrogen light in celebration of its arrival. The once dark nursery will transform into a beautiful display of colour. But even now, before that grand unveiling, the quiet glow and the carved pathways tell a profound story. In the hush of the dark cloud, a new sun has ignited its first flame, and nothing will ever be quite the same in this little corner of the universe. Though still cocooned for the moment, this infant star is on the verge of unveiling itself. Before long, its light will slip free of the last wisps of its birth cloud and take its place in the starry sky for all to see. And our protostar is not unique. All across our galaxy, in other dense clouds, countless infant stars are in this same stage. Each one remains wrapped in its birth cocoon, heralding its arrival with similar jets and outflows. In time, they too will clear their surroundings and emerge as new stars, adding their light to the cosmic tapestry. And this story is not happening in isolation. Throughout our Milky Way and in countless other galaxies, similar scenes play out. Wherever a cold cloud resides in the quiet of space, gravity and time conspire to light new stars. The universe continually conducts these silent birthing rituals, seeding the darkness with starlight, one hidden nursery at a time. For a long while, the protostar has been shining weakly, fed by the energy of its contraction and the quiet burning of a rare fuel, deuterium, a heavy form of hydrogen. Those deuterium flickers in the core act like a small pilot light, providing some warmth and pressure that temporarily slow the collapse. Still, the star in the making continues to gather mass and grow denser at its center. Deep inside, the temperature climbs steadily, millions of degrees and rising. All this time, the star remains in a delicate balance, not yet fully stable, its light still gentle and its structure still adjusting. One might imagine such a moment would come with a brilliant flash, yet it is more of a gentle awakening. Quietly, the star finds its flame. Now the moment approaches when the true fire will catch. At around 10 million degrees in the central core, an extraordinary change occurs. Hydrogen nuclei, protons, begin to fuse together to form helium. This is the ignition of hydrogen fusion, the defining source of a star's power. Unlike the brief, preliminary burning of deuterium, hydrogen fusion can be sustained and will produce immense energy. Yet when it starts, there is no grand explosion visible from outside. It ignites silently, deep within the protostar's hidden heart, like a candle quietly being lit in a distant room. The energy from this fusion fire is profound, but it builds up gradually, counteracting the force of gravity from within. As hydrogen fusion takes hold, the balance within the star shifts. The core, now releasing a tremendous outpouring of energy, pushes outward with radiation and hot pressure. Gravity, which had been relentlessly compressing the star, finds a new opponent in this internal fire. Slowly, almost gracefully, the collapse comes to a halt. The protostar ceases shrinking and settles into a stable form. It has become what astronomers call a main sequence star, a young star that shines steadily by burning hydrogen in its core. Depending on the star's mass, this milestone can arrive sooner or later. A very massive protostar might achieve its hydrogen ignition in only a few 100,000 years, racing through infancy. A much smaller protostar could take tens of millions of years to slowly shrink and heat until fusion stabilizes it. Our own sun's journey to this point likely lasted around 50 million years of gradual warming and contraction. But regardless of the timeline, eventually the same balance is reached. The long, precarious infancy is over. In its place is a shining newborn star, secure in the equilibrium between gravity pulling in and the hot pressure pushing out. With this internal transformation, the star's appearance also begins to change. Freed from the last vestiges of its cocoon, the star's light now streams out into space unhindered. The disk that still encircles the young star begins to bask in this light. Dust grains that once dwelt in darkness now gleam faintly, and they start to clump together under their own tiny gravity. In time, these will grow into rocks and eventually planets, the future companions of this star. Even as the star enters stable life, the first seeds of a planetary family are taking shape around it. The star's birth also marks the beginning of another creation. In the disk around the newborn star, particles of dust are gently colliding and sticking together. What were once microscopic motes start forming larger clumps, first the size of sand grains, then pebbles, then rocks. Slowly, over thousands and millions of years, these pieces assemble into mile-wide planetesimals, the building blocks of future planets. All the while, the young star's light has begun to bathe them, warming these infant pieces as they orbit. It's a quiet, almost invisible process, but eventually these clumps will grow into full-fledged planets circling their star. One day, perhaps, there will be worlds with oceans and mountains under the light of this sun, but that lies far in the future. For now, the planets to be are just specks and stones moving in a halo around the young sun, hidden within the luminous fog of remaining dust. Even as the star finds its steady glow, the story of its family of planets is only just beginning. Imagine witnessing this gentle arrival. One moment, the scene is dominated by the dark cloud, with only a hint of warmth seeping through its depths. Then, gradually, that hint grows into a definite light. The cavities carved by the earlier jets now serve as pathways for radiance to escape, and they widen into a clearing in the cloud. In that clearing, a star appears where none was visible before. It might still be swaddled in a glowing haze of leftover gas and dust, but its presence is unmistakable, a new point of light born where once there was only darkness. The ignition of hydrogen is not a violent outburst, but a quiet lighting from within, a soft kindling that makes the star what it is. Now, a radiant sun shines where there was previously just a collapsing cloud, marking the triumph of light and energy over the cold grip of gravity. The newborn star's glow may be bluish-white if it is very massive and hot, or golden like our sun if it is moderate, or a gentle red if it is a small, cool star. Regardless of its colour or exact brightness, it is now fully a star, a beacon in the cosmic night. All around, in the sky of its once dark nursery, one can imagine other stars undergoing similar transformations. One by one, the dark nebula is lighting up with new stars, like a cluster of campfires kindled in a dark field. The ignition of hydrogen fusion is a milestone that completes the act of star birth. Our young star has transitioned from an unstable protostar into a stable main sequence star. In doing so, it has truly earned the title of star. A star's long life can now truly begin, a steady beacon burning in the cosmic night, born quietly after ages of preparation. This soft fire in its core will define everything about it: its luminosity, its size, its temperature, and how long it will shine. From this point onward, the star will spend millions or even billions of years in this quiet, sustained burn, glowing serenely in the darkness of space. Its energy will flow outward, keeping gravity at bay, maintaining a delicate peace for eons. Each second, deep in the star's core, countless hydrogen atoms are fusing into helium, releasing energy that journeys from the core to the surface and then radiates into space as starlight. If we could watch this stellar family in a time-lapse, millions of years compressed into seconds, it would look like this. The biggest stars flare intensely, but then suddenly wink out as supernovae, leaving expanding gaseous veils. The medium stars swell and shed their skins, one by one, becoming gentle glowing cores wrapped in planetary nebulae. The smallest stars change hardly at all, twinkling steadily through the entire show. And as the cluster's siblings gradually wander apart, we'd witness these cosmic lives playing out their destinies against the slow backdrop of a dispersing nursery. Now that our star's internal fire burns steadily, the star and its siblings begin the next chapter of their existence. We have a cluster of young stars shining together in what was once a dark cloud. It's time to consider that family of light and how these stars will share their earliest years. Our newborn star is rarely born in solitude. In most cases, the cloud that formed one star has also given rise to many others. Like a brood of siblings, dozens or even hundreds of stars can emerge from the same parent cloud around the same time. In fact, the night sky's sparkling points are often members of such families, born together in clusters or loose associations. In the beginning, these stars huddle in a relatively small region of space, shining as a collective, a family of light amid the dispersing remnants of their birth nebula. Picture a newly formed star cluster. The cloud that once hid it has been thinned out by winds and radiation from its brightest members. Where there was darkness, now there's a luminous haze of gas being lit from within by a swarm of young suns. Some are massive and blue-white, blazing fiercely. Others are small and red, quietly glowing. Many are in between, warm and golden. Together they make up a glittering tapestry, perhaps visible as a hazy patch of light in the night sky, if one looks from afar. These are true stellar siblings, sharing a common origin and initially moving together through the galaxy as a tight-knit group. Within a cluster, stars are bound by their mutual gravity, but the bond is delicate. They dance around each other in slow motion, each star following its path, influenced by the gravitational pull of all the others. In those early times, they are close enough that they might affect each other's nascent planetary systems with their gravity, or bathe each other in radiation. It's a lively neighborhood. Massive stars, if present, tend to dominate the cluster's center, their intense light sculpting and even blowing away the remaining gas around them. Smaller stars, like younger siblings, often wander a bit farther out, peeking at the wider galaxy beyond the cluster's boundaries. Yet this childhood home, as beautiful and comforting as it is, will not last forever. As the cluster ages, several things happen. The gas and dust left from star formation is gradually expelled by the combined force of stellar winds and the brilliant light from the most massive members. Some of it may even be blasted out by supernova explosions when the biggest siblings reach the end of their short lives. With the gas gone, there is less mass holding the cluster tightly together. Meanwhile, the stars themselves gently tug on each other as they dance, and sometimes these gravitational interactions give a star a little extra speed, just enough to escape the cluster's hold. One by one, over millions of years, some stars drift beyond the cluster's grasp and slip away, becoming solitary travelers in the galaxy. The cluster, once a compact family, begins to expand and disperse. The process is gradual and silent. From the perspective of any single star, its closest stellar neighbors slowly grow more distant over eons. Perhaps two stars that happen to be very close become a bound pair, a binary, and they will orbit each other, remaining lifelong companions. But others wander off on solitary journeys. Imagine being on a young planet orbiting our star back in those early cluster days. The night sky above might have been ablaze with many nearby stars, far brighter than any star we see in our sky today. As time passes, those brilliant cluster mates would slowly recede into the distance. One by one, the sparkling lights would diminish, dispersing into the broader canopy of the Milky Way. The sky would still be rich with stars, but the tight, dazzling congregation would gradually loosen. Our own sun likely experienced this. It was probably born in a group with dozens or perhaps hundreds of other stars, a splendid cluster that has long since drifted apart. Now those sibling stars are scattered all over the Milky Way, far from us and far from each other, indistinguishable from any other star. Only their ages and the particular blend of elements in their makeup hint at their common origin. In fact, scientists today scour our galactic neighborhood for stars with chemical fingerprints, just like the sun's, a kind of stellar DNA analysis, in hopes of identifying these long-lost siblings among the billions. Perhaps some of the stars we see on a clear night were once next to the sun as it formed, sharing the same nursery before meandering off on separate paths. Some clusters are more tightly bound and can survive far longer. The Pleiades, for example, is a famous young cluster whose blue stars still cling together, visible as a tiny dipper-shaped smudge in the sky. In the Pleiades, one can even see a faint blue mist among the stars, a gauzy veil of dust that those stars were born from, now illuminated by their light. It is a snapshot of a stellar family in its youth, the siblings not yet fully parted. Older clusters like the Hyades have spread out more, and many clusters ultimately dissolve entirely, their members blending into the general starry background of the galaxy. Only truly massive clusters, like ancient globular clusters containing tens of thousands of stars, manage to stay together for billions of years. But the clusters that form in the disks of galaxies like our Milky Way, the open clusters and associations, tend to be transient gatherings, beautiful and short-lived on cosmic timescales, slowly evaporating into the galactic field. In this way, stars are like dandelion seeds scattered in the wind. Born together in a dense tuft, they catch a breeze, in this case, gravitational nudges and the tidal forces of the galaxy, and drift apart, spreading out into the cosmic meadow. There is a wistful beauty in this dispersal, a stellar family that must gradually part ways. Bound together at birth, yet each star must find its own path through the galaxy. It is a bittersweet aspect of their existence. Forged side by side, sharing a common beginning, but each destined to wander the vast galactic fields largely alone. Yet, even as they scatter, the imprint of their shared origin remains in each star's composition and in the quiet story it carries. Each one is a piece of that initial cluster, now lighting up a different patch of the sky. Our young star, too, will leave its siblings eventually, if it hasn't already. It will join the billions of solitary stars that roam the Milky Way, carrying on its life independently. The cluster that was its birthplace will gradually fade from memory, becoming just another part of the Milky Way's starry backdrop. But the echo of those close beginnings is etched into the star's being, an invisible thread that will always tie it to its siblings long after they've drifted apart. In time, each star drifts alone, but the echo of their shared beginning travels with them. Across the light years, an invisible kinship remains, linking them back to that common cradle in the dark. In truth, nearly every star in the night sky was born in a similar way, in the company of others. The fact that we now see so many stars scattered and solitary is a testament to the slow mixing of the galaxy over time. Each point of light above us carries the quiet history of a once crowded nursery, a reminder that even the most isolated star was born with friends. There is something profoundly humbling in this grand dispersal. One by one, the stars slip away from their nursery. But for a while, at least, they journey through the galaxy with the same age and origin, like a cohort of celestial travelers. Eventually, they may be so far-flung that they no longer recognize one another, yet in their hearts, in their very atoms, they carry the same signature of birthplace. A stellar family, once huddled together in the dark, lives on in the faint chemical echoes within each star. As our star settles into its long, steady life, one might wonder what lies ahead in the eons to come. Remarkably, much of a star's fate was sealed at that very first moment of its birth, determined largely by a single number: its mass. This one attribute, how heavy the star is, how much gas it managed to gather when it formed, acts like a cosmic fortune teller, whispering the story of the star's entire life and eventual death. In the stellar nursery, not all stars were born equal. Some emerged big and bold, containing dozens of times the mass of our Sun. Others were modest, similar to the Sun or somewhat smaller. Many more were tiny in comparison, little red dwarf stars with just a fraction of the sun's mass. Nature, it turns out, favours the small. For every one massive star that formed in the cluster, there were dozens of moderate stars and perhaps hundreds of little ones. Astronomers have a name for this statistical spread of star sizes at birth, the initial mass function, but one doesn't need the term to appreciate what it means. It means that in any newborn stellar family, the quiet majority are the faint, long-lived stars, while only a rare few are the brilliant heavyweights. Mass is the master storyteller of a star's life. A massive star lives fast and dies young. With so much weight bearing down, its core burns its fuel furiously to hold up against gravity. It pours out a tremendous light, blue-white and intense, and in a relatively short time, a few million years, hardly more, it exhausts its nuclear fuel. When the end comes for such a giant, it is spectacular. The star can no longer support its own weight, and it collapses and then explodes in a titanic supernova. For a brief moment, that single star can outshine an entire galaxy. The supernova scatters the star's elements, all those heavy atoms forged in its heart, far and wide into space, seeding the cosmos with material for new stars, new planets, and eventually new life. In fact, the iron in our blood and calcium in our bones were forged in such a stellar blast long ago, illustrating how intimately we are connected to these cosmic events. This dramatic demise is the ultimate cosmic fireworks, a grand finale that was written into the star's destiny from the moment it was born with such great mass. The aftermath of such an explosion can often be seen as a splendid nebula, a web of glowing ribbons and shells of gas racing outward. These remnants drift through space for thousands of years, gradually mixing with the interstellar medium. In their colourful haze lies the testimony of the star's life and death, and the ingredients that will nurture the next generation of cosmic structures. By contrast, a small red dwarf star lives very slowly and extraordinarily long. With so little mass, it sips its fuel sparingly and glows at a mere simmer, often too dim to be seen without a telescope from afar. Its life is one of quiet persistence, burning steadily for hundreds of billions of years. No red dwarf has yet died in the history of the universe. They burn so slowly that even after roughly 13.8 billion years, not one has exhausted its fuel. In fact, a red dwarf can shine for trillions of years, far longer than the universe has existed thus far. By the time the very first red dwarfs begin to fade, the cosmos itself will have changed in unimaginable ways. When their fuel finally does run low, eons upon eons from now, a red dwarf will not explode or collapse dramatically. It will simply fade away, gently dimming into a black ember. No explosions, no grand send-off, just a slow return to darkness, like a tiny coal quietly burning out after a very long night. Stars like our sun lie somewhere in between, neither explosive supernova titans nor eternal embers. They shine for perhaps 10 or 12 billion years. When a sun-like star nears its end, it too is guided by its mass on a different path. It will swell into a red giant, becoming a luminous but cooler star many times its original size. In that process, it will gently lose its outer layers, which drift away to form a beautiful shell of glowing gas, known as a planetary nebula, expanding outward like a delicate cosmic bubble. At the centre, the star's core remains behind as a hot, small remnant called a white dwarf, that white dwarf will quietly cool over the eons, fading like a warm ember after a fire. It's a quieter ending than a supernova, but still a dramatic transformation, a final flowering of colour and light as the star sheds its outer self, followed by a long, slow fade into the cosmic night. All these divergent paths, the brilliant supernovae, the gentle fade of red dwarfs, the ethereal glow of planetary nebulae and white dwarfs, were predestined the moment the stars were born with a particular mass. If you could measure the mass of a newborn star, you could tell, in broad strokes, which fate awaits it. The massive ones are ticking time bombs of brilliance. The modest ones, like the sun, promise a rich midlife and a gentle farewell, and the smallest whisper their light across nearly eternal timescales. Think back to our cluster of young stars shining together. In that crowd, one star might have been 50 times the mass of the sun. It blazed searingly bright and blue, dominating the cluster's light. And in only a few million years, it met its end in a ferocious supernova, perhaps compressing nearby gas clouds and triggering new stars to form as its shockwave passed by. In dying, it gave a kind of violent birth to the next generation, continuing the eternal cycle of star formation. A few other hefty stars, say 10 times the sun's mass, would last a bit longer, but still die in brilliant explosions, leaving behind exotic remnants like neutron stars, or black holes that linger in the darkness after the fireworks fade. Meanwhile, countless smaller stars, dim and red, would still be burning calmly, largely unchanged, watching those short-lived giants flare and disappear. In the vast sweep of time, those unassuming red dwarfs will far outlast and vastly outnumber their flashy siblings. It's humbling to realize that the broad outline of a star's story is essentially encoded at its birth. The galaxy is full of stars in every stage of life, and each one is following the trajectory that its mass set for it. Our own sun's mass tells us it will not explode as a supernova. Instead, it will have a gentler retirement, eventually becoming a white dwarf with a lovely planetary nebula farewell. On the other hand, somewhere in the sky tonight, a supernova may be going off, the death cry of a star much more massive, fulfilling the destiny its mass ordained. As we close this chapter of our cosmic journey, we stand at a threshold. We have watched the quiet molecular clouds give rise to shining young stars and followed their first steps into life. We have seen how, from the very start, their futures are written in the stars, in the simple number of their birth mass. Every beginning carries within it the seeds of its end. Star birth is a gentle, wondrous process, but every star that is born will one day face its own kind of death. With that understanding, we prepare to follow these stars into the next chapter of their story, one that will explore how they live, age, and eventually meet their fate, whether in quiet darkness or in cosmic fireworks that light up the heavens. Inside the heart of a star, a quiet contest holds everything in perfect balance. Gravity pulls the star's mass inward, trying to crush the core under its tremendous weight. Deep within, however, the newborn light from nuclear fusion pushes back outward, creating pressure that exactly counters the force of gravity. The result is a steady, delicate equilibrium. In this calm standoff between crushing gravity and radiant pressure, the star finds stability and peace. Though the pressures and temperatures at the core are almost unimaginably extreme, the outside of the star shines steadily and serenely. Every second, countless atoms of hydrogen fuse into helium in the core, releasing a flood of energy. This energy becomes light and heat that gradually travels outward, diffusing through layers of plasma, cooling and spreading as it goes. By the time it reaches the star's surface and escapes into space as sunlight, it has been tamed into a gentle glow. In fact, a single photon born in the sun's core may bounce and ricochet through the dense interior for tens of thousands of years before finally reaching the surface to stream outward. For the star, this balance means life. As long as the inward pull and the outward push remain equal, the star neither collapses nor explodes. It simply shines. Astronomers call this peaceful stalemate hydrostatic equilibrium, a state where each layer of the star is supported by the light and heat from below pushing upward, holding up the weight of the material above. Photons push and gravity holds. A living stillness at the core sustains the star's existence. Year after year, century after century, the star's core quietly converts mass into energy, and that energy maintains the star's steady glow. The star seems unchanging to us across a human lifetime, a constant point of light in the night sky. Inside, however, the contest of forces continues every moment. It is an ongoing miracle of balance, gravity forever trying to pull the star inward, and the star's own light pressing outward to keep gravity at bay. In this way, the star lives out the long middle chapter of its life in cosmic tranquility, burning quietly and continuously. All stars, from the smallest to the most massive, experience this phase of balanced burning. But not all stars are alike in their tranquility. Some shine hotter and bluer, others cooler and redder. To understand these differences, we must step back from the core and look at stars as a whole. We wander out of the star's heart and into the open starlight, where we can compare one star to another by their colours and brightness. In this broader view, a rich tapestry of stellar variety emerges, hinting at how each star's inner balance will play out over time. We find ourselves standing before a grand cosmic diagram, a kind of map that plots all stars by their brightness and colour. Imagine the heart-sprung Russell diagram, where each star is a point of light, placed according to how luminous it is and how hot its surface burns. High above and to the left lie the most brilliant stars, blue-white beacons, tens of thousands of degrees hot and many times the sun's size. Down below and to the right, we see the faint red glimmers of cooler stars, some so dim that they barely register to the eye. This sweeping diagonal band from bright blue to faint red is called the main sequence, and it's where stars spend roughly 90% of their lives quietly burning hydrogen. Taking a slow walk along this stellar road, we encounter a rainbow of star types. At the hot, bright end, some stars shine with a fierce blue-white intensity. These massive blue stars are extremely luminous and hot, their energy pouring out in a relentless torrent. Further along the band, the stars gradually shift to white and then yellow hues. Here we meet stars like our Sun, glowing a warm yellow-white with a surface temperature of about 5,500 degrees Celsius. They are mid-sized and steady, neither the hottest nor the coolest, living long, stable lives. Continuing our journey, the stars become orange, then red as we move toward the cool end of the main sequence. The smaller and cooler a star, the dimmer its light. At last we arrive at the red dwarfs, tiny stars that emit a gentle red-orange glow. They are faint compared to the sun, shining with only a fraction of the sun's luminosity. yet they endure with great patience, burning their fuel ever so slowly and lasting for trillions of years, far longer than larger stars. Astronomers classify this stellar diversity by assigning each star a spectral type. The types are labelled with letters O, B, A, F, G, K, and M, a sequence that runs from the hottest stars to the coolest. In simple terms, O-type stars blaze with blue-white fire. B and A stars are slightly cooler, but still white-hot. F and G stars, like our Sun, are yellowish. K stars glow in orange hues, and M-type stars are red. These spectral types encapsulate a star's temperature and light, serving as a kind of shorthand for a star's voice in the stellar choir. In this spectral chorus, each class of star speaks with its own distinct tone. The hottest O-type stars dominate with a high, energetic pitch, an intense, brilliant radiance at the blue end of the spectrum. Slightly cooler classes like A and F contribute strong, clear voices of white and yellow-white light. The mild G-type stars, including the Sun, sing in a gentle yellow tone. K and M stars, the coolest of the sequence, hum with deep orange and red light, quietly adding a soft glow to the cosmic harmony. Together, these spectral voices fill the diagram with a rich harmony of colour and luminosity. Beyond the main sequence, the HR diagram reveals other stages of starlight. Above the main band reside the giants and supergiants, stars that have left their youthful equilibrium and swollen to enormous size. Though their surfaces are relatively cool, often red or orange, they shine intensely due to their sheer vastness. Below the main band, near the lower left of the diagram, lie the white dwarfs, small, hot stellar embers that glow with concentrated heat, but only a faint light. These represent the final stage for many stars, like our Sun, tiny cores left behind after shedding their outer layers. The presence of these giants and dwarfs reminds us that stars do not stay the same forever. Yet for now, on the main sequence, each star maintains its balance and character. As we conclude our gentle tour of the HR diagram, we see how a star's colour and brightness reveal its inner nature. A star's hue, blue, white, yellow, or red, is the signature of its surface temperature, and its luminosity hints at its size or stage of life. With this understanding, we appreciate that not all stars live alike. Some burn hot and fast, others cool and slow. In the vast stillness of the galaxy, every star has its own voice and story, charted on this grand diagram for those who know how to read it. Astronomers can even gauge the age of a star cluster from its HR diagram by observing where the most massive stars have turned off the main sequence. They can tell how long the cluster's stars have been burning. In a quiet corner of the galaxy, a tiny star glows with a ruddy light. This is a red dwarf, the smallest kind of true star, burning slowly and steadily like a faint ember. Such stars are humble in appearance, far less radiant than the Sun. Up close, a red dwarf's warmth would barely light its own planetary system, and from afar, it's nearly invisible to the naked eye. Yet red dwarfs are not rare at all. In fact, they are by far the most common stars in our Milky Way, outnumbering their larger, brighter cousins. The very closest star to our solar system, Proxima Centauri, is a red dwarf, as are 50 of the 60 nearest stars to the Sun. Red dwarfs live their lives in slow motion, with masses between about 8% and 50% that of the Sun. These stars generate just a trickle of energy compared to larger stars. A typical red dwarf surface is only around 3,000 to 3,500 degrees Celsius, cooler than the sun's 5,500 degrees C glow. They shine with a soft red or orange light, quietly burning their hydrogen fuel at a glacial pace. Because they are so small and cool, red dwarfs consume their nuclear fuel extremely slowly. Their interiors are fully convective, meaning fresh hydrogen from all parts of the star cycles down into the core to be used. Nothing is wasted or left unburned in a central core, as happens in larger stars. This efficient, slow burn stretches a red dwarf's lifetime to astonishing lengths. While a star like our Sun may shine for about 10 billion years before exhausting its fuel, a red dwarf can continue glowing for hundreds of billions, or even trillions of years. None of the red dwarfs born at the dawn of the universe have had time to reach old age yet. The universe itself is simply not old enough. In the deep future, long after more massive stars have lived and died, these small red flames will still be burning quietly. They are the ultimate conservers, sipping at their hydrogen fuel slowly and steadily through cosmic eons. Despite their gentle demeanor, red dwarfs can have youthful bouts of activity. Some young red dwarfs flare dramatically, briefly brightening as they release pent-up magnetic energy. But compared to the titanic explosions of large stars, even these flares are modest flashes. For most of their existence, red dwarfs remain calm and stable, their light barely flickering. A red dwarf star could sit unnoticed in the darkness a few light years away, emitting a steady, dim glow, and we on Earth might never know it. In time, even a red dwarf's patience runs out. After trillions of years, when finally its hydrogen is all used up, the star will no longer sustain fusion. There will be no grand explosion or violent crisis. Instead, the red dwarf will quietly fade. It will contract and heat slightly, perhaps becoming a blue dwarf for a time, then gradually cool into a small white dwarf ember. But that fate lies in a future so distant it defies comprehension. For now, and for billions upon billions of years to come, each red dwarf is a small, patient flame, steadily warming the cosmic night with its faint, enduring glow. Some stars are neither small nor gigantic, but sit in the comfortable middle. Stars like our Sun. These middleweight stars live balanced lives for billions of years, shining steadily and providing warmth and light to any nearby worlds. For eons, a sun-like star quietly fuses hydrogen in its core, remaining in that stable state of hydrostatic equilibrium. But eventually, even for such a star, the supply of core hydrogen runs low. When that day comes, in about 5 billion years for our own Sun, the star begins to change in profound yet stately ways. As the core's fuel dwindles, the star must find a new balance. With less fusion energy pushing outward from the center, gravity starts to gain the upper hand. The core of the star slowly contracts under its own weight, growing hotter and denser. In response, the shell of hydrogen just outside the spent core ignites in fusion. This hydrogen shell burning produces a surge of energy that pushes outward on the star's outer layers. Gradually, those outer layers expand far into space. The star's radius swells dozens or even hundreds of times larger than it was. Its surface cools and reddens as it grows, turning into what we call a red giant star. One day, our Sun will also inflate into such a red giant, perhaps large enough to engulf Mercury and Venus, and casting its glow over Earth's sky with a ruddy light. This dramatic change is expected about 5 billion years from now, long after our time. The Sun's bloated atmosphere will likely stretch beyond the orbit of Venus, perhaps swallowing Mercury and Venus entirely. Even Earth, if it survives just at the edge of the giant Sun, will be scorched and unrecognizable under a dim red sky. Inside the red giant, the changes continue in slow motion. At the center lies an inert ball of helium ash, the accumulated byproduct of the star's earlier hydrogen fusion. The core is now very hot and under immense pressure from gravity. Eventually, when it reaches about 100 million degrees, a new spark is struck. Helium nuclei in the core begin to fuse into carbon. In a sun-sized star, this onset of helium fusion can happen quite suddenly, but then it settles into a new, steady phase. The star has found a second wind. For a time, the core's helium burns gently, producing carbon and oxygen, and the star's expansion halts. The red giant contracts slightly, glowing with a steadier yellow-orange hue. This quieter period of core helium burning is like a calm interlude in the star's late life, lasting perhaps only a few tens of millions of years, brief compared to its long hydrogen-burning youth. Eventually, the helium in the core is used up, and the star faces another transition. Now the core is filled with carbon and oxygen, elements it cannot fuse at the temperatures achievable in a mid-sized star. Fusion ceases in the core once more. Again, gravity squeezes the core tighter, and in response the star's outer layers puff outward for a second time. The star becomes an even larger red giant than before, often called an asymptotic giant branch star. In this phase, multiple shells of fusion may exist. A shell of hydrogen burning around a shell of helium burning, surrounding that hot, inert core. The star's appearance is a swollen, luminous red giant with a tenuous grip on its outer envelope. In these advanced stages, the star is enormous and diffuse, with a tiny, dense core and vast, cool layers extended around it. The outer layers pulsate slowly and begin to drift away into space, pushed by gentle stellar winds. The transformation is coming to an end. The star has quietly shed much of its mass, forming a glowing cloud of expelled gas, a planetary nebula, expanding outward into the interstellar darkness. What remains at the center is the core itself, now exposed to space. A small, extremely hot white dwarf star, no larger than Earth, but containing much of the star's original mass. It will shine for a while with residual heat, then fade over billions of years. The active life of the star is over, concluded not with a bang, but with a beautiful, peaceful unveiling of the core. In this way, a sun-like star's journey from youthful brightness to gentle old age and final repose is marked by serene transformations. A slow blossoming into a red giant and a quiet casting off of its outer layers, illuminating the cosmos one last time with a pastel shell of starlight. Not all stars conclude their lives so gently. Behold the monarchs of the stellar realm, the massive stars of brilliant blue and white fire. These stars are titans, dozens of times more massive than the Sun, and millions of times more luminous. Their surfaces seethe at tens of thousands of degrees, and their cores burn with ferocious intensity. A massive star lives fast and dies young. It pours out energy at such a prodigious rate that it will exhaust its central fuel in only a few million years. A mere blink of an eye in cosmic time. During that brief lifetime, it reigns as a dominant beacon in its region of the galaxy, its radiance outshining lesser stars, and its stellar winds shaping the surrounding nebulas with authority. From the moment a massive star ignites, it undergoes a headlong rush through its life stages. It swiftly burns through hydrogen in its core, fusing it into helium far more rapidly than a smaller star could. The tremendous energy output creates an outward pressure that holds up the star's great mass, but just barely. On the stellar surface, this energy drives an intense stellar wind, streams of charged particles blowing outward at millions of kilometers per hour. These winds carry away the star's outer material over time. The most massive stars, in fact, lose a significant fraction of their mass through steady winds and occasional giant eruptions. It is as if the star is both shining and evaporating at the same time, a blue-hot torch throwing off its own substance as it burns. Yet even as it sheds mass to space, the star's core continues forging heavier elements at a furious pace. After only a few million years of core hydrogen fusion, the center runs low on fuel and begins to contract, just as in smaller stars. But everything happens faster. The core heats up further, and helium fusion ignites promptly, refilling the core with carbon and oxygen. In a massive star, there is no gentle, drawn-out retirement phase. It transitions rapidly from one fuel to the next. Once helium is depleted, the star begins burning carbon into heavier elements, then neon, oxygen, and silicon in turn. Each successive stage of fusion yields heavier nuclei and releases tremendous energy, but each stage also burns faster than the last. A process that might take a sun-like star millions or billions of years is compressed into mere centuries or days in a supergiant star. In its final throes, a massive star may fuse oxygen and then silicon for only a matter of months, weeks, or even days. It is a desperate last sprint toward the finish line, as the star's core fills up with iron, the heaviest ash of all, in an extremely short time. Throughout these furious changes, the star expands and contracts, often becoming a red or yellow supergiant as the outer layers respond to the increasingly complex burning within. A star that was once blue-white and hot may swell into a red supergiant, like Betelgeuse, its surface cooling and reddening even as its core burns hotter than ever. Other massive stars might shed their outer hydrogen layers entirely and reveal a blazing helium core. Whether in blue or red attire, these stellar monarchs experience instability as they near the end. They may pulsate or undergo eruptions, and their powerful radiation and winds continue to carve the surrounding space, sculpting cavities and blowing bubbles in the gas and dust of their birth clouds. Deep inside, the core's burden grows. In layers like an onion, shells of fusion surround an iron core that no longer produces energy. This iron core is the heavy heart of the massive star, the final product of its furious nucleosynthesis. Iron cannot be fused into anything heavier without consuming energy, so once the core is largely iron, the star's nuclear fires can only fade. For a brief moment, gravity and pressure maintain an uneasy balance, but the star's fate is sealed. In that heavy heart of iron, the story of the massive star's life is about to reach a dramatic climax. The colossal star has burned its candle at both ends, shining with incredible brilliance and forging new elements in its core. And now it stands on the brink of a violent end. In the cosmos, no star is truly an island. Many stars come in pairs, locked in graceful orbit around their common center of mass. These binary stars live together, each influencing the other's evolution in subtle and sometimes dramatic ways. Imagine two suns dancing around each other in the depths of space, a celestial pas de deux. As long as both stars are relatively small and well separated, they may age independently, each following its solo life cycle. But if the stars are close, or of very different masses, their fates become entwined. The companionship can become a cosmic tug-of-war, and the usual rules of stellar evolution change. Consider a binary system, where one star begins to age faster than its partner. As the more massive star exhausts its core fuel and swells into a red giant, its outer layers balloon outward toward the companion. Eventually, the gravity of the smaller companion may begin pulling those outer layers away. Gas pours from the giant star toward its partner, forming a bridge of material between them. In astronomical terms, the giant star overflows its Roche lobe, the region of space where its gravity dominates, and matter streams toward the companion. What was once a solitary star now finds itself donating mass, like a swollen river spilling into a neighboring valley. This mass transfer dramatically alters both stars' destinies. The giant star, losing its envelope, is stripped down to its inner core much sooner than it would have been on its own. It may stop short of the usual red giant finale and instead become a smaller, hotter star, perhaps a helium-burning core, or even a premature white dwarf. Meanwhile, the companion star gains fresh fuel from its partner's sacrifice. Swallowing this mass often causes the companion to spin faster and burn brighter, effectively rejuvenating it. The smaller star can masquerade as a much younger star thanks to its newly acquired fuel, defying the expectations set by its age. The result is a reversal of roles. The once massive star becomes a shriveled remnant, while the once smaller companion shines more fiercely with its ill-gotten gains. Binary mass exchange can lead to exotic outcomes. Some pairs eventually merge entirely, uniting into a single star after a spiraling embrace. Others remain separate, but end up in unexpected states. For example, a massive star might lose so much mass to its companion that it never undergoes a supernova, quietly becoming a white dwarf instead. Or a star that would have been a modest red giant might bulk up from accreted mass and go supernova when it otherwise would not have. In the twilight of a binary system, one star often evolves into a dense remnant, a white dwarf, neutron star, or black hole, while the other is still a normal star. The remnant can gravitationally draw matter from the living star, leading to spectacular events. A white dwarf siphoning gas from a companion can ignite the stolen fuel in sudden nova flashes, or if it amasses enough, detonate entirely in a type of supernova, a thermonuclear explosion that can outshine a galaxy. Neutron stars and black holes can pull gas from companions as well, heating it to X-ray hot temperatures and forming swirling accretion disks, the telltale sign of X-ray binary systems. And if two stellar corpses, such as neutron stars, merge together, they can unleash tremendous explosions and even bursts of gravitational waves, literally shaking the fabric of space and time. These cataclysms forge some of the heaviest elements in the universe, a final cosmic creation born from the death spiral of a binary pair. Through these interactions, binary stars showcase nature's capacity for change and adaptation. The presence of a companion alters the straightforward path a star would have followed alone. It is a reminder that in the universe, relationships matter. Even stars, in their grand and predictable lifespans, can have their stories rewritten by the influence of a close partner. In the delicate dance of binary stars, mass and energy flow from one to the other, and both stars are forever changed. Their shared fate is a complex duet, a paired destiny, illustrating that the life of a star is not only determined by its mass and composition, but also by the company it keeps. Even solitary stars can be full of surprises. Some stars do not shine with a steady glow, but instead beat like a cosmic heart, growing brighter and dimmer in a regular rhythm. These are the variable stars that seem to breathe. During each cycle, the star's outer layers slowly expand and then contract again, causing its brightness to rise and fall. To an observer, it is as if the star is inhaling and exhaling light. A classical Cepheid variable, for example, might brighten over a couple of weeks, then fade over the next few weeks, only to repeat the pattern over and over with clockwork precision. In fact, certain stars periodically swell and shrink, as if they were literally breathing in and out. The mechanism of these pulsations lies in the star's interior. As layers of gas heat up, they become more opaque and trap energy until pressure builds and pushes the layers outward. Then the gas cools, becomes transparent, and the star's gravity pulls it back in. This repeating process creates a stable oscillation, a natural resonance that can persist for millions of cycles. Different variable stars have different tempos. Some giant red stars take many months to complete a cycle, their variations gentle but noticeable. Smaller pulsating stars, like RR Lyrae variables, beat faster, changing in a matter of hours or days. Cepheid variables, perhaps the most famous, typically have periods ranging from a few days to a couple of months. In all cases, these stars keep time in their own way. Each pulsation, a slow, steady heartbeat that echoes across space. The regularity of certain variable stars has made them invaluable cosmic timepieces. Over a century ago, astronomer Henrietta Leavitt discovered that Cepheid variable stars follow a simple rule. The longer their period, the more intrinsically luminous they are. This means that by observing a Cepheid's pulsation period, astronomers can deduce its true brightness, and from that, its distance. Cepheids became known as standard candles, helping map the scale of the universe. In the 1920s, astronomer Edwin Hubble measured Cepheid periods in the Andromeda Nebula and proved it was actually a distant galaxy far outside our own, a discovery that expanded the known universe. A Cepheid in a distant galaxy can be observed to blink steadily, and its rhythm reveals how far away that galaxy lies. In this way, the rhythmic beats of Cepheid stars have served as a cosmic yardstick, extending humanity's reach across space. There is a poetry in the way these stars behave. In dark stretches of sky, a variable star can be seen waxing and waning like a lighthouse beacon, keeping cosmic time. The entire galaxy is sprinkled with these stellar metronomes, delicate, ceaseless pulsations that remind us of the dynamic nature of stars. Even our sun exhibits subtle oscillations, though not enough to markedly change its light, a faint echo of the more dramatic pulsations of its variable cousins. By watching variable stars, we witness a conversation between a star's gravity and its light, a push and pull that creates a cosmic melody. In the grand stillness of space, the stars that breathe add a gentle rhythm, a reminder that even in quiet, there is motion and cadence throughout the universe. After a long life of shining, whether steady or in pulsation, a star's approach to death brings new kinds of change. The final acts of a star's life are often heralded by the shedding of its outer layers, a kind of celestial sigh as the star prepares for its end. In its waning years, a sun-like star begins to lose its outer layers through steady, gentle winds. Over millennia, it expels vast amounts of gas and dust into space, leaving behind a hot, exposed core. The cast-off material, illuminated by the core's ultraviolet glow, forms a planetary nebula, a glowing shell of gas marking the star's farewell. Such nebulae often take on haunting shapes, like rings or hourglass lobes, sculpted by the outflowing gas. It is as if the star, in its final breaths, creates a cosmic artwork to signal its passing. Massive stars, too, shed layers in their final stages, though on a more violent scale. A blue supergiant, or luminous blue variable, may erupt sporadically, blasting portions of its outer layers into space in colossal outbursts. One famous massive star in our galaxy underwent a great eruption in the 19th century, ejecting giant lobes of gas that now enshroud it, a spectacular prelude to its eventual demise. Even without eruptions, massive stars drive fierce stellar winds that only grow stronger as death nears. By the end, a massive star may have already shed much of its mass. In both low-mass and high-mass stars, these final outflows shape the circumstances of the star's death. The expelled gas enriches the surrounding space with the heavy elements it forged, seeding the surrounding space for future generations of stars and planets. For the dying star, the loss of mass can seal its fate. A lighter remnant might become a white dwarf quietly, whereas a heavier core, no longer held in check by the mass it has shed, is poised to collapse dramatically. In a sense, the star's last winds and eruptions clear the stage for what comes next. The delicate nebula, drifting away from a sun-like star, presages the cool white dwarf ember that will remain. The dense shell around a supergiant stands as both a product of the star's life and raw material for the fireworks to come. As we reach the end of this long burning phase, we find each star at the brink of transformation. The quiet shedding of a planetary nebula and the furious gusts around a supergiant are both preludes to an ending. The star has sculpted its own memorial in gas and dust. Soon, either in a gentle fade or a catastrophic explosion, the stellar drama will reach its conclusion. The stage is set for the final cosmic fireworks that will mark the true death of a star. At the core of a dying star, an uncanny silence falls. For ages, the star has burned bright, forging element after element in concentric shells around its core, like the layers of an onion. Lighter elements fused into heavier ones, each stage shorter than the last, and each releasing heat to hold gravity at bay. But now, at the centre, the fire has reached an impasse. Iron. Iron is the end of the line, the ash of nuclear burning. Instead of fueling further fusion, iron steals energy. Trying to fuse iron would consume energy rather than release it. For the first time in the star's life, its core produces no energy. The thermonuclear fires gutter out, leaving a dense iron heart supported only by momentum and pressure from earlier burning. Outwardly, the star might still appear unchanged, its hot glow betraying nothing of the crisis within. But in that core, the balance between pressure and gravity has tipped. With no new heat to push back, gravity begins to tighten its grip on the iron core. The threshold has been reached in silence, a quiet, fatal pause before the inevitable collapse. Then, suddenly, the bottom drops out of the star's core. In a final instant, literally less than a heartbeat, the iron core can no longer bear its own weight and begins to implode. Gravity pulls the core inward in a runaway collapse. Freed from any opposing pressure, the core matter hurtles downward at a significant fraction of the speed of light, the infalling mass compressing and heating as it goes. As the core implodes, Temperatures soar to incredible levels. Floods of gamma-ray photons are released, so energetic that they start to undo the work of 1 million years of fusion in milliseconds. These gamma rays slam into iron nuclei and shatter them back into lighter elements, essentially ripping the core's heavy atoms into fragments. This violent process, called photodisintegration, devours energy and accelerates the collapse even further. In the crush, protons and electrons are squeezed together and merge into neutrons, releasing a burst of neutrinos, nearly massless particles streaming outward in staggering numbers. In mere moments, the core that was once the size of Earth compresses to only tens of kilometers across. At densities exceeding those inside an atomic nucleus, matter reaches an unyielding stiffness. The collapse finally halts as nuclear forces abruptly repel further squeezing. The innermost core actually bounces, a neutron-rich ball that rebounds and slams into the still collapsing layers above it. This impact launches a fierce shockwave racing outward through the infalling material of the star. But the struggle isn't over yet. Initially, the shockwave stalls against the star's outer layers, losing energy as it plows into the infalling gas. Here neutrinos come to the rescue. Countless neutrinos streaming out of the core suddenly deposit a fraction of their energy into the stalled shock. Normally neutrinos hardly interact with matter, but in the crushing density of the core, a few do get trapped behind the shock. Their energy heats and pressurizes the region, giving the shock a much-needed boost. The revived shockwave surges outward with new strength. Now nothing can stop the explosion. The rejuvenated shock tears its way through the star's layers. As it plows outward, the shock's intense heat and pressure fuse atoms into new, heavier elements. In seconds, forging elements beyond iron that the star could never make during its lifetime. Gold, silver, uranium, and more are created in this brief furnace and seeded into the expanding fireball. After only a few hours, the blast reaches the star's surface and blows the star apart. A supernova is born, announced by a sudden flash of light and an expanding shell of debris racing into space. In the aftermath, a tiny dense core remains, where the heart of the star once lay. Depending on the star's bulk, this core becomes either a neutron star, a city-sized sphere of degenerate matter, or, if enough mass fell in, a newborn black hole hiding at the center of the dispersing devastation. This compact remnant is the final memento of the star, left behind amid an expanding cloud of gas and stellar ash. For massive stars, this is the deadly finale, a core collapse supernova triggered by iron's silent rebellion. Yet there is another path to cosmic catastrophe, one that involves a far smaller star and a very different kind of explosion. Not every stellar blast is driven by a collapsing core. Some are detonations, thermonuclear flash fires that consume a star in seconds. This alternative route to destruction occurs in the quiet husks of sun-like stars, white dwarf stars that have long burned out and await a violent reignition. Picture a white dwarf star, a hot, Earth-sized cinder left over from a sun-like star, quietly orbiting a companion. In some cases, that white dwarf steals matter from its neighbor, slowly growing heavier. If it reaches a critical mass, around 1.4 times the Sun's mass, something astonishing happens. The pressure and temperature in its carbon-oxygen core become extreme, and as it approaches this Chandrasekhar limit, nuclear fusion ignites anew. But unlike a normal star, the white dwarf cannot regulate this burning. It's supported by electron degeneracy pressure, so when the fire sparks, the star doesn't gently expand and stabilize. Instead, it triggers a runaway reaction. In the blink of an eye, a fusion flame front races through the white dwarf's interior. Carbon and oxygen that have been inert for eons burn in a furious flash. Within a couple of seconds, the entire star detonates. The thermonuclear blast releases an enormous amount of energy, on the order of 1044 joules, enough to unbind the star completely. No part of the white dwarf remains intact. It is transformed into an expanding fireball of superheated plasma and newly forged elements. For a brief time, this type of supernova, known as a type Ia, rivals the brilliance of any core collapse explosion. In fact, it can be even more uniform in its peak light. Because the explosion is triggered at a critical mass threshold, many type Ia supernovae reach nearly the same peak luminosity when they explode. Their consistent brightness allows these events to be used as standard candles to measure distances to their host galaxies. By comparing how bright they appear to how bright they truly are, astronomers in the late 1990s discovered something astonishing. Distant type Ia supernovae were dimmer than expected, leading to the revelation that the expansion of the universe is accelerating, driven by a mysterious dark energy. In essence, nature offers two grand ways for a star to meet its end: a colossal implosion of a massive star's core, or a sudden thermonuclear incineration of a small degenerate star. Both yield a supernova's extraordinary burst of light, forging new elements and outshining entire galaxies in their prime. But even among supernovae, there are extremes. On rare occasions, a dying star's explosion is not just a supernova, it is a hypernova, unleashing far more energy, often focused into narrow jets. These are the fiercest stellar farewells, often signaling the birth of a black hole and giving rise to long-duration gamma-ray bursts. For a hypernova, the progenitor star is thought to be enormous and fast-spinning. When its core collapses, instead of settling for a neutron star, it likely forms a black hole. In the process, the collapsing star's rotation and intense magnetic fields channel some of the infalling mass into twin beams that blast out of the star's poles. These jets are launched at nearly the speed of light and punch through the star's outer layers. The hypernova releases on the order of 10 times the energy of a typical supernova, making it one of the most energetic explosions in the universe. If one of those relativistic jets is aimed toward Earth, we observe a gamma-ray burst, an intense flash of high-energy radiation. Long-duration gamma-ray bursts, lasting more than about 2 seconds, are believed to signal these hypernova explosions. To an observer in the jet's path, the collapsing star becomes a blinding beacon. For a few fleeting seconds, it can outshine almost everything else in the universe. The initial burst of gamma rays may last only moments, but in that instant, it releases a titanic amount of energy, rivaling the output of millions of stars. Such gamma ray bursts are fleeting, but they are followed by afterglows that can linger for days or weeks. After the initial flash, the jets slam into the surrounding interstellar gas, generating shockwaves that emit X-rays, visible light, and radio waves. Astronomers who catch a GRB quickly swing their telescopes to its location to witness this fading afterglow. By studying the afterglow, they can pinpoint the burst's host galaxy and often find signs of an accompanying supernova. In 2003, for instance, a long gamma-ray burst in the constellation Leo, GRB 030329, was found to coincide with the appearance of a hypernova, a type Ike supernova, SN 2003DH, from a massive star's collapse. Such observations cemented the link between long GRBs and the deaths of massive stars. For observers on Earth, gamma-ray bursts are some of the most distant and ancient signals we detect. Some have travelled for billions of years across the universe. In fact, One GRB detected in 2009 originated when the universe was only about 630 million years old, just a few percent of its current age. These bursts serve as beacons across time, allowing us to study stars that died in the early epochs of the cosmos. We catch their final flash billions of years later, a message from the deep past that massive stars were already living and dying in the young universe. Yet there are other stellar cataclysms that push the envelope of brightness. Astronomers have discovered supernovae so exceptionally bright that they are classified as superluminous supernovae, events 10 or more times more luminous than a normal supernova. These superluminous supernovae, SLSNE, shine with outsized brilliance, often for a longer duration than typical supernovae, leading to unusually broad and long-lasting light curves. Their sheer luminosity poses a puzzle. What could be powering such an extraordinary display? It seems that SLSNE may not all share the same origin. A few different exotic mechanisms can produce them. One leading hypothesis involves the most massive stars in existence, on the order of 100 or more times the Sun's mass. In these behemoths, an astonishing process can occur. The core becomes so hot that high-energy gamma photons spontaneously convert into electron-positron pairs. This drains pressure from the core, causing it to partially collapse, which then ignites a catastrophic thermonuclear explosion that blows the star to bits. This is called a pair instability supernova. The star is completely obliterated, leaving no remnant behind. Pair instability supernovae are expected only in extremely massive, low metallicity stars, conditions thought to be common in the early universe. Initially, scientists predicted that such explosions would be almost unimaginably bright, perhaps hundreds of times a normal supernova. But more recent models suggest their peak luminosities, while huge, might be only a few dozen times that of a normal supernova. A notable example candidate is SN 2006 GY, one of the most luminous supernovae ever observed, which may have been a pair instability explosion of a monstrous star. In that case, the star's core didn't just collapse into a neutron star, it blew itself apart outright in a runaway thermonuclear blast. Another model for superluminous supernovae invokes a very different power source, a central engine in the form of a newborn magnetar. Imagine the core of a massive star collapsing and leaving behind an extremely magnetized, rapidly rotating neutron star. If this magnetar spins with a millisecond period and a magnetic field hundreds of billions of times stronger than Earth's, it can act like a cosmic dynamo. As it slows its spin, it pumps energy into the ejected supernova material, keeping it hot and luminous far longer than usual. In effect, the magnetar's rotational energy is transferred to the explosion, boosting the brightness to extraordinary levels. In many magnetar-powered scenarios, the supernova ejecta have little or no hydrogen. The star likely shed its outer layers before exploding. This matches the hydrogen-poor spectra of many observed superluminous supernovae. The magnetar's energy keeps the debris hot and glowing longer than normal, giving a broader, more prolonged peak in the light curve. This model has successfully explained a number of the most luminous events observed. However, not every superluminous supernova fits neatly into either the magnetar or pair instability mold. Some cases show peculiar properties that still puzzle researchers. It's possible that other factors are at play. For instance, the explosion's blast may be colliding with a dense shell of gas around the star. Or perhaps some unknown process is contributing to the immense energy. These outliers keep the field rich with questions, reminding us that we have more to learn about these cosmic lighthouses. To untangle these extraordinary explosions, and indeed any supernova, Scientists rely on the information carried by light itself. Every supernova is an ephemeral beacon, and encoded in its light are clues to its nature. By dissecting that light through spectroscopy, and by charting the supernova's brightness over time, astronomers can decode the physics at play, the way the light brightens and fades, and the specific colours and spectral lines it contains form a kind of stellar autopsy report that skilled observers can interpret. When astronomers discover a new supernova, they immediately take its spectrum, spreading its light into a rainbow of wavelengths to see the dark absorption lines and bright emission lines within. Those spectral lines are signatures of elements. If prominent lines of hydrogen appear, that tells us the exploding star still had a hydrogen-rich outer layer, marking the event as a Type II supernova. If no hydrogen lines are seen, it falls into the Type I category. Among Type I supernovae, a particular absorption line of singly ionized silicon, around 615 nm wavelength, is the hallmark of a Type Ia supernova. If that silicon line is absent, but lines of helium are present, we classify the event as Type Ib. If both hydrogen and helium lines are missing, we call it Type Y. These spectral fingerprints act like signposts to the nature of the explosion. Hydrogen lines mean the star retained its envelope. Helium, without hydrogen, implies a star that was stripped down to its core. A strong silicon line means a white dwarf detonation. The spectrum also reveals velocities. Supernova ejecta rush outward at incredible speeds, and their spectral lines are broadened by the Doppler effect. We often see supernova lines smeared out over a huge range of wavelengths, corresponding to expansion speeds of thousands or even tens of thousands of kilometers per second. A supernova can expel matter at a few percent of the speed of light g, and we read that in the broad, shifted lines in its spectrum. As the supernova evolves, its spectrum changes. Early on, right after the explosion, the spectrum may be extremely hot and blue, with only a few broad absorption lines from the outermost layers. But over days and weeks, the ejecta expand and cool, and deeper layers become visible. For a Type II supernova, one might see the character of its hydrogen lines change from ionized to neutral as the gas cools and recombines. Later, in the nebula phase of the supernova, the spectrum is dominated by emission lines from elements like oxygen, calcium, and iron in the thin, expanding gas. By tracking these changes, astronomers effectively perform a time-lapse autopsy of the shattered star, peeling away layer after layer. The supernova's color and brightness over time, its light curve, provide another dimension of clues. A Type Ia, supernova's light curve, shows a sharp rise and then a steady decline over months, powered by the radioactive decay of nickel-56 to cobalt-56 to iron-56. Essentially, a Type Ia glows as a nuclear afterglow, the decaying nickel providing the energy. A Type IIp plateau supernova, on the other hand, often has a different light curve shape. It rises to peak and then stays at a nearly constant brightness for several weeks, a plateau, before fading. That plateau is caused by the energy released as hydrogen in the star's extended envelope recombines, sustaining the luminosity for a while. By comparing these light curve behaviors, astronomers can distinguish what kind of supernova they are seeing, even without a detailed spectrum. Through these observations, spectra, light curves, color evolution, astronomers reconstruct the chain of events in the explosion. We identify what elements were present and newly synthesized, how fast the star's guts were blown out, and clues to the progenitor's nature. Was it a red supergiant or a compact white dwarf? Each spectral line or light curve feature is like a sentence in the story of the star's death. By reading them carefully, we translate the fleeting flash of a supernova into a physical understanding of stellar evolution. In recent decades, astronomers have begun observing supernovae with new eyes beyond traditional telescopes. Light, from radio waves to gamma rays, still carries most of the information, but other elusive messengers also accompany a star's death. A collapsing star's core doesn't only shine in light, it also unleashes floods of ghostly neutrinos and even ripples in spacetime, gravitational waves. To truly capture a star's final moments, we must listen for these faint signals as well, the neutrinos and gravitational waves that race out from the dying core. Neutrinos are nearly invisible, ghostly particles that hardly interact with matter. Yet a collapsing stellar core unleashes an almost unimaginable flood of them. Roughly 99% of the energy of a core collapse supernova is carried away by neutrinos streaming out of the core. These neutrinos escape the star with ease, rushing outward at nearly the speed of light. They race outward long before the star's shockwave, or any light, can break free. While photons struggle to emerge from the dense stellar interior, neutrinos pass through it effortlessly. By the time we see a supernova's light, a huge burst of neutrinos has already come and gone, a silent herald of the explosion. Those neutrinos are direct messengers from the star's collapsing core. In February 1987, a blue supergiant star exploded in the Large Magellanic Cloud, a companion galaxy to our Milky Way. Hours before astronomers saw any light from this supernova, SN 1987A, underground detectors in Japan and the US registered a sudden burst of neutrinos. About 24 neutrino interactions were observed, a tiny fraction of the trillions that flooded out of the star, but it was enough to confirm a core collapse. For the first time, humans had directly detected the ghostly signal from an exploding star's heart. This neutrino detection from SN 1987A was a landmark moment. It confirmed that neutrinos carry off the bulk of a supernova's energy, and it offered a glimpse into the core collapse process in real time. Notably, the neutrinos arrived at Earth hours before the supernova's light became visible, essentially giving astronomers an advance warning that the star had collapsed. It was our first true multi-messenger observation of a supernova. Neutrinos and light observed together, with the neutrinos heralding the event. Those 1987A neutrinos were a faint whisper from the collapsing core, telling us that a neutron star was forming and that our theoretical picture of supernova collapse was on the right track. Since then, no other supernova has occurred close enough for us to catch its neutrinos, but our readiness to detect them has grown. Today, huge neutrino observatories, like Super Kamiokande in Japan and IceCube at the South Pole, keep vigilant watch. They are linked in a network called SNEWS, Supernova Early Warning System, which will alert astronomers instantly if a sudden influx of neutrinos is detected from a stellar collapse. If a supernova explodes in our galaxy, thousands of neutrino interactions could be recorded in these detectors, providing an unprecedented view into the core collapse process as it unfolds. While neutrinos let us glimpse a collapsing core, another potential messenger is gravitational waves. According to Einstein's theory, any violent, asymmetrical motion of mass can create ripples in spacetime. Gravitational waves. A collapsing star's core, especially if it's spinning, turbulent, or off-center, should emit a brief storm of gravitational waves as it implodes and rebounds. These waves would carry unique information from deep inside the core, essentially the vibrations of the star's destruction. So far, we have not detected gravitational waves from a supernova. None has occurred close enough since our detectors came online. Current observatories like LIGO and Virgo could catch a burst if a supernova happens in our galaxy, and future upgrades will improve our chances. Scientists have modelled the potential wave signatures. Each explosion mechanism would imprint a distinct pattern on the waves. For example, a neutrino-driven collapse might yield a faint, brief signal, whereas a rotation-powered one could produce a stronger, longer-lasting wave. If we managed to detect such waves from a supernova, we could probe the cause dynamics in a way that neither light nor neutrinos can. While we have yet to hear a supernova's gravitational song, the universe has provided other dramatic gravitational wave events. In 2017, astronomers observed gravitational waves from the merger of two neutron stars, an event that also produced a burst of gamma rays and a glow called a kilonova. This was the first time both gravitational waves and light were seen from the same event. The neutron star merger's kilonova, faintly visible in the days after, was powered by the creation of heavy elements like gold and platinum in the collision's debris. That spectacular observation proved that multi-messenger astronomy can enrich our understanding. Gravitational waves told us about the motions of merging stellar remnants, and electromagnetic waves told us about the matter flung out and the elements formed. Similarly, when we one day detect gravitational waves from a supernova alongside neutrinos and light, we will have a complete triad of messengers to study the death of a star from every angle. Even without modern instruments, humans have been witnessing supernovae for millennia in their own way. Throughout recorded history, sudden new stars in the sky have been noted in chronicles and journals. Ancient Chinese astronomers meticulously documented guest stars, unaware that they were observing stellar explosions. Medieval European scholars, Arabic astronomers, Japanese and Korean observers all left accounts of these transient stars. The earliest suspected observation of a supernova may be recorded in a 5,000-year-old rock carving, possibly depicting a strange guest star in the sky. Moving into recorded history, the first clear documentation comes from Chinese astronomers in 185 AD. They noted the appearance of a guest star that shone for 8 months before fading away. This object, now identified with the supernova remnant known as RCW86, is likely the earliest supernova ever recorded by humanity. For ancient skywatchers, a new star that persisted for months was something noteworthy, even ominous, and they carefully recorded it. Over the following centuries, other supernovae left their mark in history. In the year 1006, observers across China, Japan, the Middle East, and Europe witnessed a brilliant new star, likely the brightest supernova ever recorded. Historical accounts describe it casting shadows and even being visible in daylight. In 1054, another famous guest star was recorded by Chinese and Japanese astronomers, and possibly noted in Native American petroglyphs. This one, in the constellation Taurus, was so bright it could be seen in the daytime for weeks. Unbeknownst to those who saw it, they were witnessing the explosion that created the Crab Nebula, a supernova remnant that astronomers study to this day. Moving forward, the supernovae of 1572 and 1604 in our own Milky Way were pivotal in the history of astronomy. In November 1572, a brilliant new star burst forth in Cassiopeia. Danish astronomer Tycho Brahe observed it closely for months, noting that it had no measurable parallax, so it was far beyond the Moon in the realm of the fixed stars. He published his findings in a treatise titled De Nova Stella, on the new star. The very word nova, Latin for new, comes from this observation, though we now distinguish supernovae from the much smaller novae. Tycho's supernova shone as bright as Venus at its peak, then gradually faded over about 16 months. Just 32 years later, in October 1604, another startling new star appeared in the constellation of Ophiuchus, observed by Johannes Kepler, among others. Kepler's supernova similarly showed no parallax, confirming it was a distant stellar phenomenon. These events challenged the prevailing Aristotelian belief that the heavens were unchanging. If new stars could appear and then fade, the cosmos was not the immutable realm it was once thought to be. Today, we have identified the remnants of those historical supernovae. The expanding cloud of debris from the 1054 event is the Crab Nebula, which glows strongly in radio, optical, and X-rays and harbours a pulsar, the neutron star left from the explosion. Tycho's 1572 supernova remnant and Kepler's 1604 remnant have been imaged by modern telescopes as faint, expanding nebulae, still bearing the names of those astronomers. Even the remnant of the 10,006 supernova has been detected as a wispy shell of gas. These are echoes of explosions witnessed by people long ago, physical proof that the new stars they recorded were real events. Not only do we find evidence in the sky, we also find it under our feet. In recent decades, scientists have discovered traces of supernova debris embedded in Earth's geological record. In particular, a rare isotope called iron-60 has been detected in deep ocean crusts and sediment cores. Iron-60 is not naturally produced in significant amounts on Earth. It is created in supernova nucleosynthesis. The deposits suggest that around 2 to 3 million years ago, Earth was sprinkled with a fine dusting of supernova fallout. A star, perhaps 100 or so light-years away, exploded, and radioactive iron atoms eventually drifted through space and settled on Earth, where they became locked in seafloor minerals. This amazing discovery means a supernova's footprint is literally embedded in Earth's rocks, providing direct evidence that such an explosion happened relatively nearby in the not-too-distant past, geologically speaking. Such findings have even spurred hypotheses that supernovae have affected life on Earth. The timing of that supernova, 2.8 million years ago, intriguingly coincides with climatic and faunal changes in the late Pliocene epoch. Some researchers speculate that cosmic rays from the nearby explosion might have increased cloud cover or subtly altered Earth's climate, perhaps contributing to conditions that encouraged human ancestors to adapt and evolve. While these ideas remain debated, they underscore the point that stars, in dying, can influence planets and life in unexpected ways. In the grand scheme, supernovae are the universe's way of recycling matter and energizing evolution. The dramatic deaths of stars seed space with heavy elements and trigger new generations of stars. Every one of us carries atoms, like the iron in our blood, that were forged in a supernova long before Earth formed. By studying these bright endings, we are not only learning about stars, but also about our own origins. As we gather all these threads, the facts deciphered from supernova light, the neutrino and gravitational wave whispers, the traces left in human lore and even in Earth's crust, we see that a star's death is both an end and a beginning. The brilliant funeral of a star enriches the cosmos with elements that will become part of new stars, new planets, and maybe new life. The remnants left behind, whether neutron star or black hole, are gateways to extreme physics and sometimes new cosmic phenomena. The story continues. From death comes rebirth. In the next part, we will follow the journey onward, exploring how these remnants shape their surroundings and give rise to new wonders as the cosmic cycle of starbirth and star death rolls on. In the aftermath of a supernova, The darkness of space is littered with glowing shrapnel. Where once a star shone, now a vast cloud of debris spreads outward, drifting through the cosmic night. Threads of incandescent gas stretch like tendrils of a celestial flower, delicate and glowing. These filaments trace the outlines of the exploded star's remains, forming a beautiful, eerie tapestry against the void. Shock waves race ahead of the debris, unseen but powerful, sculpting the interstellar gas into shells and knots. Each shock front plows through space like a ripple through a cosmic sea, compressing and heating everything in its path. Behind the shock, the stellar shrapnel expands more slowly, cooling and recombining into vivid nebular clouds. We witness a scene both violent and serene, the star's final breath billowing outward, lighting up the surrounding space in transient neon-bright hues. The once fierce blast wave gradually softens, slowing over centuries, but its imprint remains, a faintly glowing remnant that will persist for millennia. Time passes, and the supernova remnant blossoms in slow motion. What began as a furious flash becomes a tranquil cosmic bloom. Thin filaments of gas, rich with new elements, float outward like spider silk. They intertwine to form intricate lace-like patterns, illuminated by the energy still coursing through them. Clumps and knots of denser material shine brightly where shock-heated gases cool and condense. These wispy structures bear witness to the star's explosive end, petal-like arcs and tendrils spreading tens of light years across. In some places, the shock front creates a nearly spherical shell, as if the star's ghost is blowing a bubble into the galaxy. In other places, the expanding debris is uneven, shaped by the star's surroundings or the asymmetries of the blast, giving the remnant a ragged, beautifully irregular form. The darkness between the filaments is filled with X-ray hot plasma, invisible to human eyes, but there, a silent haze of million-degree gas slowly cooling. Within these remnants, change is constant, yet subtle. As the gas expands, it sings a silent song, the faint emission of atoms recombining, of electrons spiraling in magnetic fields. We see it as a gentle glow, hydrogen shining soft red, oxygen glowing ghostly green, sulfur and neon adding their own spectral notes. Each filament is a story in light, telling of the elements the star forged in its life and death. This glowing tapestry drifts through the interstellar medium, stirring that medium as it goes. The shock wave from the explosion continues to push on the gas ahead, sending a ripple of compression farther and farther out. When it encounters denser clouds in space, it can squeeze them, triggering new births, the seeds of future stars. Thus, even as a star dies, it sends out a pulse that may awaken new stars in the surrounding nebula. The remnant is not merely debris, it is fertile cosmic soil, enriched by heavy elements and stirring the galaxy with its expanding shock front. Over hundreds and thousands of years, the supernova remnant grows and transforms. Initially, the expansion was rapid, material racing outward at thousands of kilometers per second in a free expansion. Now, it begins to sweep up as much mass from space as it ejected. A snowplow effect takes hold. The accumulated gas forms a dense shell at the forefront, while the interior remains a hot, tenuous bubble. This shell is thin but brilliant, its edge marked by shining ribbons where gas cools and radiates energy away. As it cools, the shell's shock front weakens, and the remnant slows to a more stately pace. Eventually, after tens of thousands of years, the once distinct boundary fades. The remnant's gases merge back into the general interstellar medium, leaving behind only a gentle memory. A subtle mix of elements and a faint whisper of turbulence contributed to the galaxy's ever-churning seas. But for now, in its youth and middle age, the supernova remnant remains a spectacular cosmic bloom, the shrapnel of the star in full bloom, painting the sky with the gorgeous aftermath of destruction. Amid this expanding glow, not everything is dispersed. At the heart of many such remnants lies a surprise left behind by the explosion. Where once the star's core resided, there may be a tiny, incredibly dense object spinning amidst the wreckage. As the filaments of the nebula slowly drift outward, one pinpoint of light in the center flickers rhythmically. It is here that we encounter one of the universe's most extraordinary lighthouses, a neutron star, the collapsed core of the star that died. Like a cosmic beacon amid the fading embers, it spins and shines, heralding the next chapter of this stellar afterlife. In the silent depths of the shattered star, a small but mighty remnant turns with unthinkable speed. A neutron star, barely 20 kilometers across, remains where the core once was, a city-sized cinder left from a sun that spanned millions of kilometers. It is unimaginably dense. Crush a mountain into a marble, and you begin to grasp its density. Indeed, a single teaspoon of neutron star material would outweigh a mountain, or even an entire human population. This tiny sphere spins rapidly in the dark, completing a rotation in mere fractions of a second, or perhaps a few seconds. As it spins, it emits beams of radiation from its magnetic poles, twin searchlight beams sweeping across space. If one of those beams crosses Earth's line of sight, we detect a pulse of radio waves, X-rays, or light at regular intervals. And so, the neutron star reveals itself as a pulsar, blinking steadily like a far-off lighthouse on a cosmic shore. Imagine drifting in space, light years away, and seeing nothing but the faint glow of a supernova remnant's clouds. Suddenly, a quick flash of radio energy washes over you, then another and another, a perfectly timed sequence like the ticking of a celestial clock. That is the pulsar's beacon, spinning with astonishing precision. Some pulsars rotate dozens of times each second, their beams sweeping past us hundreds of times per minute with metronomic regularity. These spinning neutron stars are the universe's most reliable timekeepers. In fact, their rotational stability rivals the finest atomic clocks. Over years, their pulses arrive so predictably that astronomers can use them to map gravitational waves passing through space, or even to navigate spacecraft by their signals. Each rotation of the pulsar is the collapsed core's heartbeat, a beat that barely slows even over millions of years, except for occasional tiny stutters known as glitches, when the starquake-like adjustments make the pulsar skip a beat before resuming its steady song. The environment on a neutron star is beyond extreme. The gravity at its surface is so strong that if you dropped an object from 1 meter above, it would hit the surface in a microsecond, accelerated to thousands of kilometers per second. Yet, we perceive the pulsar not by its gravity, but by its light and radio emissions, which are powered by intense magnetic fields. A neutron star's magnetic field is typically trillions of times stronger than Earth's, funneling charged particles toward its magnetic poles. There, particles are whipped around and accelerated, emitting focused beams of radiation, the pulsar beams. These beams swing around as the star spins, much like the spotlight of a lighthouse turning through the fog. From Earth, we catch these beams if the orientation is just right. The pulsar appears to blink on and off with each rotation. In the darkness of space, these blinks are a cosmic Morse code, each pulsation a testament to a star's death and uncanny afterlife. To the human imagination, a pulsar can be likened to a cosmic lighthouse or a phantom pulsating heart in the sky. The term lighthouse of the deep, fits perfectly. These objects reside in the deep sea of space, often hidden in nebula or far-off corners of the galaxy, yet their beams reach across thousands of light-years. They guide astronomers to new discoveries. We first found pulsars as mysterious radio pulses that were so regular. Some wondered if they were signals from an intelligent civilization. Now we know they are natural, yet they still feel almost artificial in their precision. They spin down extremely slowly, losing a tiny bit of energy over eons. But while young, their spin can be incredibly fast and stable. Some pulsars, called millisecond pulsars, have been revved up by binary companions and rotate hundreds of times per second, becoming even steadier, as steady as time itself. These millisecond pulsars tick so regularly that we could set our clocks by them. In a peaceful night sky, the notion that a small, dense star is whirling around hundreds of times in the time it takes to blink your eye is a mesmerizing thought. Deep in their cores, neutron stars are made mostly of neutrons, subatomic particles squeezed together by gravity to an extreme degree. It's as if the core of the original star has been compressed into a giant atomic nucleus. The material is exotic, possibly with superconducting particles and ultra-high pressures. But on the outside, we witness mostly the magnetized, spinning shell emitting those beams. And sometimes, those magnetic fields and rapid spins combine to produce something even more exotic. For while many neutron stars shine steadily as pulsars, a rare few are prone to outbursts and flares, unlike anything else. Their magnetic fields so intense that they twist and snap, causing mighty starquakes. These are the magnetars, an even more mysterious lighthouse, whose light can turn fiercely bright and dangerous in an instant. As we continue, the gentle ticking of a pulsar gives way to the occasional crack of thunder from a magnetar, a reminder that even in cosmic afterlives, there are quiet beacons and there are tempests of magnetism waiting to be unleashed. Most neutron stars are content to spin quietly, emitting their beams in a steady rhythm. But a small fraction are born different. Magnetars, the most magnetically charged objects in the cosmos. A magnetar is a neutron star with a magnetic field hundreds or even 1,000 times stronger than that of an ordinary pulsar. If a typical neutron star is an electrified lighthouse, a magnetar is a magnetic maelstrom contained in a sphere just a dozen miles wide. In the calm of space, magnetars normally appear unassuming, perhaps emitting a soft glow of X-rays as they rotate slowly, once every few seconds. But beneath that calm exterior, titanic forces are at play. The magnetic field of a magnetar is so incredibly strong that it can distort atomic structures in its vicinity. Within 1,000 kilometers of a magnetar, the very atoms are stretched and squeezed by magnetic forces. Chemistry as we know it breaks down under these conditions. If a magnetar were somehow placed halfway to our moon, its magnetic field could erase every credit card on Earth and disrupt every electronic device. A mind-boggling thought, considering that distance is over 100,000 kilometers. These are magnets that defy comprehension, millions of billions of times stronger than the magnets we encounter on Earth. The life of a magnetar is full of stress and tension. Its magnetic field, twisting through and around the star, puts immense strain on the solid crust of the neutron star. Imagine the crust, a rigid, crystalline layer of ultra-dense nuclei, being contorted by magnetic forces far beyond any steel being bent by hand. Eventually, something must give. At unpredictable times, the crust cracks in a sudden starquake. In that brief moment, the magnetic field reconfigures explosively, releasing a gigantic burst of energy. The magnetar, which may have been quietly spinning and barely noticed except in X-rays, suddenly flares with high-energy radiation. X-rays and gamma rays burst out, and for a few seconds, the magnetar can outshine almost everything in the sky in those wavelengths. These are the tempests of magnetism, ferocious storms contained in a tiny star. On Earth, we have actually detected such magnetostorms. On December 27, 2004, a magnetar halfway across the Milky Way let out a flare so powerful that it briefly altered Earth's upper atmosphere. In that moment, for a fraction of a second, this distant object was the brightest source of gamma rays in our sky, overwhelming our satellites. It was as if a star had screamed, and though it was 50,000 light-years away, we heard its echo. Despite these outbursts, magnetars are relatively short-lived phenomena. Their magnetic fields decay over a period of perhaps 10,000 years. In the cosmic timeline, that's the blink of an eye. Magnetars live fast and die young. As the field decays, the star calms. It no longer has the energy to produce powerful flares, and it might settle into life as a more ordinary neutron star. Yet, during their brief existence, magnetars leave an indelible mark. Sometimes their outbursts create expanding nebula rings around them, shells of material blasted off the star's surface by the starquake. One magnetar was observed to have a glowing ring of gas around it, likely debris from a past flare. And there is speculation that magnetars might even be connected to other cosmic mysteries. The incredibly bright but brief fast radio bursts, FRBs, seen from distant galaxies. In 2020, a known galactic magnetar produced a millisecond burst of radio energy, so intense that it suggested magnetars could indeed cause FRBs. It seems that in their death throes, stars continue to surprise us, sometimes by turning into these volatile magnetic giants. Yet, there is a gentle side to explaining these immense fields. We can picture it like this. The neutron star's core collapse wound up its magnetic field the way a tight spinner winds up thread. The star's rotation and convection right after birth amplified the field to unimaginable levels. Now, the magnetar is like a tightly coiled spring of magnetism. When it releases energy, it is that spring unwinding just a bit. During quiet periods, the magnetar might seem almost peaceful, a rotating ember in the darkness, emitting a steady X-ray glow as it cools. It's only when the tension snaps that we are reminded of the behemoth lurking in that tiny sphere. The physics is complex, but we can imagine the magnetar's field reaching out into space, making the vacuum itself behave oddly. Near a magnetar, empty space isn't truly empty. Its magnetic field is so strong it can polarize light, splitting photons, turning vacuum into a kind of prism. It may deform atoms into needle-like shapes. These are things straight out of theoretical physics, yet they are real in magnetars. Listening to the cosmos, magnetars might be considered the occasional peals of thunder amid the steady chorus of pulsar chirps. They remind us that even in the afterlife of a star, after the explosive supernova, there can still be fireworks. Theirs are just invisible to our eyes, mostly in high-energy rays. But the effect can be sensed across space. After a magnetostorm passes, the star quiets down again, as if nothing happened. The cracked crust reseals under gravity's immense pressure, and the beacon continues rotating. Perhaps only a faint afterglow in X-rays lingers for a while. The universe returns to its relative calm, until the next quake. Magnetars highlight one path of a star's core, intense, short-lived magnetism. But there is another path, especially for the most massive of stars, where even neutron star physics fails to hold the line against gravity. There are times and places in the cosmos where gravity wins so completely that even light cannot escape. For some stellar cores, the collapse does not stop with a neutron star. It continues, and the result is the darkest of all remnants, a black hole. When a truly massive star dies, sometimes all that remains is an invisible gravitational trap. The core collapses not into a solid neutron star, but into something even more extreme, a black hole. In these cases, gravity has won outright, crushing the core beyond any known state of matter. What forms is a region of space so warped that nothing, not even light, can climb out from within a certain boundary. This boundary is called the event horizon, often thought of as the black hole's surface, though it's not a surface in the traditional sense. It's an eerie concept, a sphere of pure darkness, a one-way membrane through which matter and light fall inward, but cannot return. At the centre, we believe, lies a singularity, a point of infinite density, the final product of gravity's triumph, though our physics cannot fully describe it. For our journey's purposes, it is enough to stand at the event horizon's edge and contemplate what it means. Where gravity wins, even starlight is trapped, orbiting or falling inward endlessly. The black hole is the ultimate stellar afterlife, a silent pit, cradling light in a lethal embrace. Picture the core of a star, perhaps 25 times the mass of our sun, collapsing in on itself. The outer layers have blown away in a brilliant supernova, but the core, weighing a few times the sun's mass, keeps falling inward. For an instant, it might become a neutron star, but it's too heavy, too irresistibly drawn in by its own gravity. In a fraction of a second, that core shrinks past the neutron star stage. Any resistance by the neutrons succumbs. The core's mass compresses into an ever smaller volume until it vanishes from view behind an event horizon. All the mass is still there, of course, a few solar masses worth, but now it's confined in a space no wider than a small town. The newly formed black hole might be, say, 30 kilometers across if we measure its horizon's diameter. Outside that horizon, the gravity is intense, but not infinite. A nearby object could orbit safely if it keeps its distance. Inside, however, space and time themselves have collapsed into something we cannot observe. For any matter left near the core at the moment of collapse, it's like falling off a cliff with no bottom. Despite this dramatic formation, a newborn black hole itself doesn't emanate much directly. There is no light from the black hole, by definition. It is simply a dark spot in space. If some material from the exploded star falls back into it, or if the star's collapse was more gradual, we might see a flash of gamma rays as the black hole forms, sometimes thought to cause certain gamma ray bursts. But otherwise, in many cases, the black hole is stealthy. It announces its presence only by how it affects its surroundings. Gas that falls toward it will swirl into a hot accretion disk, emitting X-rays as it spirals in. If the black hole is spinning, it might also produce jets, narrow beams of particles shooting out along its poles, which can light up the nebula around it. For a moment, consider what a scene that would be. A supernova remnant lit not just by the glowing filaments of ejected gas, but also by a faint, central disk, funneling material into an invisible hole, possibly with twin jets of energy piercing outwards. It's a quieter aftermath than a pulsar or magnetar at the center. Often, a black hole can sit silently with no fanfare if it has nothing to devour. It becomes like a hidden puppeteer, only noticeable by its gravitational pull on nearby stars or gas. The phrase, "horizons that cradle light," evokes a poetic image of what happens around a black hole. At a certain distance from the black hole, light can actually orbit. This is called the photon sphere. Imagine a ray of light that passes close enough. Instead of flying off into space, it gets caught, circling the black hole perhaps once or a few times before either escaping or falling in. In a sense, the black hole's gravity cradles this light in a tight orbit. Closer in, just outside the event horizon, light might swirl around multiple times. But once it crosses the horizon, it's lost to the outside universe, forever part of the black hole's mass energy. It's a strange cradle, indeed, one from which nothing is ever gently set back down. Yet, as destructive as black holes seem, they too play a role in the cosmos. They are efficient engines for converting infalling matter into energy, in the form of jets and radiation, affecting their surroundings. And as endpoints of stellar evolution, they are part of the galactic ecosystem. Over millions of years, a black hole might drift through space, occasionally gulping gas or stray stars, but otherwise simply persisting. Even though we cannot see a black hole directly, humanity has now managed to visualize one, indirectly. In recent years, telescopes combined to capture the silhouette of a supermassive black hole in galaxy M87, and later the one at our own galaxy's center. Those images show a ring of light, the photon orbit, and hot gas around the black hole, with a dark center, which is the shadow of the event horizon. Scale that down to a stellar black hole, and you can imagine if we were close enough with the right instruments, we'd see a tiny ring of light marking where photons orbit a void. It's a majestic and unsettling sight, essentially the shadow of gravity itself. For smaller black holes formed from stars, no direct images exist yet, but their effects are measured. They tug on companion stars, producing X-ray emissions in binary systems. They merge with each other, creating ripples in spacetime that we now detect as gravitational waves, as was done for the first time in 2015. Every time two black holes collide, it's the final afterlife chapter for both stars that made them. A new, larger black hole is born, and energy in the form of gravitational waves spreads out, gently shaking the fabric of the cosmos. From the quiet darkness of black holes, we turn to something much more tangible and golden. Black holes and neutron stars, in their own ways, set the stage for one of the universe's grandest acts of alchemy. The violence of their formation, whether a supernova or the collision of two such remnants, forges elements heavier than iron, scattering them across the galaxy. The cosmic alchemy performed in these moments is what creates the precious metals and rare elements that speckle planets and living beings. To truly appreciate that, we must follow the story of those new elements as they are created and cast out into space, destined eventually to become part of new worlds. In the heart of stellar explosions and stellar collisions, the universe has hidden its forge of creation. Stars spend their lives fusing lighter elements into heavier ones. Hydrogen to helium, helium to carbon, oxygen, and so on. But this process grinds to a halt at iron. Iron is the nuclear ash that a star's core cannot burn for energy. So when a massive star explodes as a supernova, it provides the extreme conditions needed to push beyond iron. For a few brief seconds, as shockwaves reverberate through the dying star's core, a flurry of nuclear reactions occurs. Neutrons are captured at a furious rate by atomic nuclei, a process aptly named the R process, or rapid neutron capture process. In those moments, elements like silver, gold, iodine, uranium, and many others are synthesized. The detonation hurls them outward, along with all the other debris. A single supernova might produce planets' worth of iron and sulfur, and trace amounts of the heavier treasures. The debris, enriched with these fresh elements, expands into space. Cosmic alchemy has occurred. Elements that did not exist in the star's peaceful days have now been forged in the crucible of its death. But supernovae are not the only smithies in the cosmic workshop. In recent years, astronomers observed an even more exotic event: two neutron stars spiraling into each other and merging. These catastrophic collisions, called kilonovae, are like supernovae in miniature, but incredibly rich in neutron-rich matter. When two neutron stars collide, their merging ejects a significant amount of extremely neutron-heavy material that undergoes the R process. The result is a bloom of heavy elements. We believe this is where a large fraction of the universe's gold, platinum, and other heavier stable elements are made in abundance. Unlike the bright, blue-white light of a typical supernova, a kilonova's glow is often described as reddish or golden, as the freshly minted heavy elements in the ejector absorb and re-emit light in complex ways. In 2017, scientists detected both gravitational waves and light from a neutron star merger in a galaxy about 130 million light-years away. The signal carried the spectral fingerprints of elements like strontium, direct evidence that such a collision had synthesized heavy matter. Imagine, in that distant galaxy, an immense flash, not just of light, but of newly created gold and rare earth elements flying out into space, to be incorporated into future planets or moons. This cosmic forging of elements is profoundly connected to us. Every atom of gold in your jewelry, every bit of iodine in your thyroid, every precious metal in our electronics. Many of those atoms were birthed in a supernova explosion or a neutron star collision that occurred long before the Sun and Earth formed. We carry within us the ashes of stellar alchemy. It's a humbling thought. The calcium in our bones and the iron in our blood once formed inside a star. The gold adorning a ring might have been flung out in the merger of two ultra-dense stellar corpses. Through these violent ends come new beginnings, the chemical enrichment necessary for rocky planets and for life itself. Before the first generation of stars exploded, the universe had only the lightest elements. It took countless stellar lives and deaths to stock the periodic table with the diversity we see today. In each supernova remnant drifting through a galaxy, there is a treasure trove of elements that will one day seed new worlds. Consider one particular heavy element, say uranium. It requires such extreme conditions to form that it likely can only be made in significant quantities during our process events. Yet, billions of years ago, some star or merger created uranium and scattered it into space. When our solar system was coalescing out of a cloud of gas and dust, those uranium atoms, along with gold, platinum, and others, were mixed in. They ended up in the Earth's rocks, contributing to our planet's internal heat through radioactive decay, and in humanity's mines, where we eventually found them. Or consider gold, scattered likely by neutron star collisions, which then drifted, uncombined, until being trapped in young planets like Earth as flecks in ore veins. Every heavy element tells a similar story, a chain of custody that begins in a stellar catastrophe and ends in the solid matter of a planet, or perhaps the biology of living creatures. As the supernova remnant expands and cools, these new elements begin a journey. At first, right after the explosion or collision, everything is an incredibly hot gas. Atoms are ionized, flying freely. But as the gas cools over years and centuries, atoms start to bind together. Some form simple molecules, others stick to tiny solid surfaces, forming dust grains. This is where the next chapter of creation begins. The dust, molecules, and cosmic rain that will eventually gather into new celestial bodies. The heavy elements forged by cosmic alchemy are not meant to remain as hot plasma forever. They will eventually settle and join the grand cycle of star formation once more. We now venture into that gentle, crucial phase of cooling and condensation, as the fiery debris of a star's death becomes the seeds of future stars and planets. The fire of the supernova fades, and in the twilight of the aftermath, cooling begins to dominate. The once scorching plasma, millions of degrees hot, has expanded and radiated its energy away into the vastness of space. Now, over years and decades, the gas temperature drops enough for recombination. Electrons find protons to form hydrogen atoms again. Ionized metals capture electrons to become neutral atoms. This is a pivotal time, for as the gas cools to thousands of degrees and below, something magical occurs. Molecules start to form. Two atoms of oxygen meet and bond to form O2, or an oxygen atom finds a carbon to make CO. Hydrogen atoms, so abundant, pair up into H2 molecules. These molecules are important coolants. They radiate away heat efficiently, allowing the gas to chill further. Within the expanding supernova remnant, pockets of gas become cool enough that they might drop below a few hundred degrees, and at those temperatures, even more complex molecules can appear, perhaps water, H2O, or others, clinging to dust. Meanwhile, certain atoms begin to condense into tiny solid grains. Elements like carbon, silicon, iron, and others can crystallize into specks of dust, mere nanometers or micrometers across. Imagine soot or fine sand forming spontaneously in the nebula. That is cosmic dust, the raw material from which planets can eventually grow. These dust grains are like cosmic pollen, drifting on the interstellar breeze. They are small, but they carry a lot of significance. They often have layered structures, with cores of mineral, silicates maybe, and mantles of ices or frozen gases that collect as the grains travel through colder regions. Dust is also highly efficient at cooling the gas further. Grains absorb the energy of collisions and re-radiate it as infrared light. Additionally, dust provides surfaces on which molecules can form. For instance, two atoms of hydrogen might find each other on a dust grain and combine into H2, something they rarely do in empty space. Thus, dust and molecules work in tandem to transform a hot plasma into a cold, dark cloud. It's as if the remnants of the star are creating their own night, transitioning from the bright fireworks of the explosion to the murky clouds that herald new beginnings. As more time flows, centuries, millennia, the supernova remnant becomes increasingly difficult to distinguish from any other patch of interstellar cloud. It has expanded and cooled so much that what was once an eye-catching nebula may blend into the background gas of the galaxy. But the key difference lies in its composition. This region of space is now enriched with heavy elements and dotted with dust grains that did not exist before. It's a patch of the galaxy that is especially fertile. Astronomers have observed sites where past supernovae have likely triggered the formation of new stars by compressing nearby molecular clouds. In the aftermath of death, there is the promise of rebirth. The cooled remnants gas can begin to collect under its own gravity or contribute to larger molecular clouds. Within those larger clouds, some dense clumps might begin to contract and ignite new stars. The dust, carrying elements like silicon and carbon, will be incorporated into the swirling disks around those newborn stars, forming the building blocks of planets, comets, asteroids. All the solid pieces of a new solar system puzzle. One can think of the process as a gentle cosmic rain. Just as water vapor in the air cools and condenses into droplets that eventually fall as rain, so too does the hot gas condense into molecules and dust that will rain down gravitationally into new worlds. Sometimes literally, astronomers speak of interstellar rain when material from supernovae later falls into forming protostars. The heavy elements and dust grains become seeds within cold molecular clouds, and when a new star forms, often a disk of gas and dust forms around it. From that disk, planets will accrete. So perhaps, in a poetic sense, the supernova remnants dust is rainfall for the next generation, nourishing the birth of planets and maybe life. Take, for example, our own solar system. There is evidence in meteorites that a nearby supernova exploded right around the time our sun was forming. Traces of short-lived isotopes like aluminum-26 in primitive meteorites suggest that debris from a supernova mixed into the cloud that became the sun and planets, possibly even triggering the collapse of our solar nebula. If true, that means a supernova's death throes directly influence the formation of our home. The dust and molecules from a long-dead star became part of the Earth, part of us. Now consider the journey of a single dust grain formed in a supernova. It solidified in the cooling ejecta, perhaps as a tiny crystal of silicon carbide or a flake of graphite carbon. This grain, no larger than a smoke particle, is ejected out at thousands of kilometers per second, but soon encounters drag and slows relative to the expanding remnant as it plows into interstellar gas. It survives the shockwaves. Many grains will be shattered, but let's follow one that lives. After a few thousand years, the grain finds itself drifting in the general interstellar medium, separated from the now dispersed remnant, wandering through space along with billions of other grains. It might float for millions of years, maybe getting incorporated into a cold molecular cloud. In that cloud, it could be coated with water ice, ammonia, methanol, forming layers of frost and organic molecules on its surface. If that cloud later forms stars, our grain may end up in the accretion disk of a protostar. There it could stick together with other grains, gradually building into a pebble, then a rock. Perhaps it becomes part of a comet or an asteroid in a new solar system. Eons later, that comet might rain down on a young planet, delivering water and organics, contributing to the ingredients for life. All from one speck, birthed in a star's violent end. This cosmic rain cycle links the death of stars to the genesis of life-giving planets. As we envision this cooling remnant full of dust motes and molecules, it appears as a dark, quiescent cloud, illuminated faintly by surrounding starlight. But even in this calm, there are ghostly travelers zipping through. While most of the energy of the supernova has by now dissipated in light and heat, some of it has taken another form. High-speed particles that were accelerated by the blast. These particles, electrons, protons, atomic nuclei, are still racing away from the scene at nearly the speed of light. They have become cosmic rays, invisible, fast-moving shards of the explosion's energy, now journeying through the galaxy. To us, the cloud may seem peaceful, but passing through it, and indeed through us, here on Earth, are countless cosmic rays from long-ago supernovae. Thus, from the hushed dust and molecular rain of a remnant, we turn to these energetic messengers, the rays that emanate from the ruins of shattered stars. High above Earth, and threading through the solar system, come particles moving at relativistic speeds. Cosmic rays arriving from all directions. Many of these are born in the shock waves of supernova remnants, making the remnants not only beautiful clouds, but also powerful accelerators. When the supernova exploded, Its shock front drove into the interstellar medium, and as it did so, it acted like a giant natural particle accelerator. Charged particles caught in the shock's turbulent magnetic fields got bounced back and forth, gaining energy with each pass, a process scientists call Fermi acceleration. Over time, some particles achieved incredible energies and then escaped the shock to wander the galaxy. These are the cosmic rays, principally protons, nuclei of hydrogen, and heavier nuclei, and some electrons, all travelling at nearly the speed of light. In essence, even after the light of the supernova fades, these high-energy travellers continue the star's story, carrying away a fraction of its energy in kinetic form. Imagine standing on the fringe of a supernova remnant. The visible filaments are far away, and you might think nothing else is there. But unseen to your eyes, a proton whizzes past at 99% of light speed, having been flung out of the remnant's shock front, perhaps a few hundred years after the explosion. It will roam the galaxy for millions of years, maybe bending this way and that under galactic magnetic fields, until one day it might strike the atmosphere of some planet, perhaps our Earth. When it does, it collides with air molecules, producing a shower of secondary particles and a flash of light high in the atmosphere. On Earth, we see these as fleeting streaks in cloud chamber experiments, or detect them with specialized telescopes. They are literally pieces of a distant star's fury, arriving long after that star is gone. The cosmic rays are mostly harmless to us at the flux that reaches ground, but they contribute a bit to background radiation. High in space, astronauts and electronics feel their effect more strongly. Over geologic time, some scientists speculate that cosmic ray flux variations could influence Earth's climate or mutation rates by affecting the atmosphere or directly damaging DNA. In any case, they are a form of cosmic weather, an ongoing drizzle of energetic particles from events long past. Supernova remnants have been identified as major sources of galactic cosmic rays by multiple lines of evidence. For instance, the remnants shine in very high-energy gamma rays, indicating collisions of accelerated protons with ambient gas, producing pions that decay into gamma photons. It's an invisible but essential aspect of the remnant. Not only is it a nebula to behold, it's also akin to a cosmic particle cannon. Some remnants, like the one from a supernova observed in 1006 AD, have shock waves still accelerating particles up to the knee of the cosmic ray spectrum, around 10^15 eV energies. Others, like the famed Crab Nebula, which came from a supernova in 1054 AD, accelerate electrons to high energies, which produce intense synchrotron radiation, a form of non-thermal glow in X-rays and radio. The Crab's central pulsar powers that acceleration, making it a bit of a special case. But generally, the expanding shells of remnants do the job. Picture the shock front of a remnant moving at thousands of kilometers per second, ploughing into the thin interstellar gas. Ahead of it, the magnetic field in the galaxy is relatively steady. Behind it, in the turbulent wake, the magnetic field is chaotic and amplified. Protons can bounce between these regions, crossing the shock, then being reflected by irregularities, crossing again, each time gaining a little speed. After perhaps hundreds or thousands of such bounces, the proton attains a speed extremely close to light. At some point, it finds a chance to fly out of the region entirely. Off it goes as a cosmic ray, leaving the remnant behind. Over tens of thousands of years, countless particles do this. The remnant thus effectively leaks energy in the form of cosmic rays, contributing significantly to the pool of high-energy particles in the galaxy. Without supernovae, space would be a calmer place in terms of radiation. With them, space has this persistent background of rays that can influence star formation chemistry. Cosmic rays ionize hydrogen in cold clouds, influencing molecule formation and radiation levels around stars. These cosmic rays, though themselves invisible, sometimes make their presence known in beautiful ways. When they strike Earth's atmosphere near the poles, they can spur additional ionization that aids in creating the aurora's shimmering curtains. Though most aurora is from solar particles, cosmic rays add a minor note. Some cosmic rays even reach the ground or get trapped in minerals, creating rare isotopes like carbon-14 in our atmosphere, which living organisms incorporate. So in a sense, bits of ancient supernovae are intertwined with the fabric of life. Carbon-14 dating, for example, relies on an isotope produced partly by cosmic ray bombardment of nitrogen in the air. Think about this. Every second, cosmic ray particles pass through your body. Most are harmless, but each one is a whisper from a cataclysm that might have occurred millions of years ago and light years away. They connect us to those distant events. In a very real sense, the rays from the ruins of stars ensure that the influence of a supernova does not end at the edge of its remnant. It propagates across the galaxy. The cosmic rays eventually diffuse out of the Milky Way, seeding intergalactic space with energetic particles. Some of the highest energy cosmic rays likely come from even more powerful events, like hypernovae or active galactic nuclei. But at least up to a point, ordinary supernovae suffice. We have journeyed with the star from its explosive death to the diffusion of its remains and energies across space. By now, the star that was is thoroughly transformed. Its matter is scattered as glowing filaments that cool into dust and gas. Its core remains have become exotic objects, neutron stars or black holes. Its energy has dispersed as light, as cosmic rays, as shock waves that trigger new stars. But one more astonishing possibility remains to explore. Even after such a titanic explosion, even after a star dies, there can still be worlds in orbit around the remnants. Planets, those embodiments of stability and gentle orbit, have been found in these most unlikely of places, circling neutron stars and white dwarfs. Could it be that life, too, might find a foothold in these strange environments? We end this part of our journey by contemplating these strange companions, the planets and disks that accompany stellar remnants, and what possibilities they hold. It sounds like the setup for a fantastical tale. Planets orbiting a pulsing corpse of a star, or a world circling a black hole, or a cold white dwarf. Yet science has revealed that such systems exist. The first exoplanets ever discovered, in fact, were found around a pulsar. In 1992, astronomers were astonished to find small, rocky planets in orbit around PSR B257+12, a rapidly spinning neutron star. This pulsar, a light-housing remnant of a supernova, has at least 3 planets, one of them with mass comparable to Earth's. Imagine a sky from one of those planets. The Sun is a tiny neutron star, perhaps emitting a dim glow in X-rays and a wind of energetic particles. There is no bright daylight as we know it. The star is more like a beacon, possibly with twin beams sweeping across the sky if you could see in radio or high-energy light. The planet is bombarded by intense radiation with every pulse. It's an unlikely harbour for life, to put it mildly. The environment is drenched in the pulsar's wind of high-energy particles and radiation. Yet, the mere existence of these planets suggests that even in the violent aftermath of a supernova, a sort of second generation of planetary systems can arise. How do such planets come to be? Perhaps they are survivors, once orbiting the original massive star. Somehow they weathered the supernova blast. More likely, they formed from the debris disk around the neutron star after the supernova. Indeed, after some supernovae, a portion of the ejected material falls back and forms a disk around the neutron star. Over time, that disk can cool and coalesce into planets. Essentially, a miniature planetary system born from stellar ashes. The pulsar PSR B1257 plus 12's planets are named rather hauntingly: Drauga, Poltergeist, and Phobetor, echoing their ghostly nature around an undead star. Life on such worlds would be extraordinarily challenging. Any atmosphere could be stripped by the pulsar's radiation unless it was incredibly thick. Yet, theoretical work has even speculated on habitable zones around pulsars. If a planet were massive enough, a super-Earth, and had an atmosphere millions of times thicker than Earth's, it might convert the deadly radiation into heat and sustain liquid water on its surface, albeit under a heavy blanket of atmosphere. Conditions would resemble the bottom of Earth's ocean in terms of pressure, shielding life from radiation. It's a far-fetched scenario, but fascinating. Life clinging on in a dark, perpetual storm, warmed by a pulsar's faint energy. White dwarfs, the remnants of sun-like stars, also offer homes to planets. These stellar embers are small, Earth-sized, and initially very hot, though dim due to their size. Over billions of years, they cool and fade. But we've detected a giant planet orbiting a white dwarf named WD 1956 plus 534. This Jupiter-sized planet orbits extremely close, so close that a year there lasts only about 1.4 days. How could a planet be so near a star that must have been a red giant before collapsing? It likely moved inward after the star became a white dwarf. Or perhaps it's a remnant core of a planet that survived the giant phase. Whatever the case, it shows that planetary companions can endure a star's transformation into a white dwarf. Many white dwarfs also show evidence of having had asteroids or minor planets. They have polluted atmospheres, meaning heavy elements, calcium, magnesium, iron, show up in their spectra, likely from debris that fell onto them. This suggests that these white dwarfs have disks of dust and rock, remains of planets or asteroids, around them, which occasionally accrete onto the star. In some cases, we've even seen the remains of what might be disintegrating planets or asteroids orbiting white dwarfs, like one white dwarf where a small object is clearly breaking apart and forming a debris ring. It's both melancholic and hopeful. The star's original planetary system was mostly destroyed during the red giant phase, and yet some pieces linger on, and a few lucky worlds might survive at a safe distance or form anew from the rubble. Now consider black holes and planets. If a star that had planets turns into a black hole through a direct collapse or after a supernova, what happens to those planets? If they were far enough away, they might remain in orbit, largely unaffected except for the loss of the star's light. Gravity is gravity. Replace the Sun with an equal mass black hole, and Earth's orbit would barely change, though Earth would freeze and go dark. So theoretically, a planet could orbit a stellar mass black hole. The scene would be surreal. The planet would have no sunlight, just the blackness of the black hole, plus maybe a faint glow from an accretion disk if any material is still falling in. The sky might show an unusual gravitational lensing effect. Distant stars and galaxies warped into rings or arcs as their light bends around the black hole. If there were a nearby star, that star's light could bend around the black hole to provide a distorted illumination at times. In science fiction, such planets have been imagined, with perhaps life surviving by geothermal energy or a dim red dwarf companion star in the system. We haven't detected any planets around black holes yet. They would be very hard to detect. But it's not outside the realm of possibility for some to exist, especially in multi-star systems, where one star becomes a black hole and others remain to provide light. The idea of quiet disks refers to those leftover or second-generation accretion disks around neutron stars or white dwarfs or even black holes that could give rise to planets. These disks are quiet in the sense that after the initial fireworks of the star's death, they settle into a relatively stable, thin disk of material that's not extremely hot or luminous, unlike the roaring accretion disks of actively feeding black holes. A quiet disk around a neutron star might be composed of gas and dust that fell back after the supernova. Over tens of thousands of years, it cools and molecules form, similar to a scaled-down version of a protoplanetary disk. Eventually, coagulation of dust can lead to planetesimals and then planets. It's a slow, quiescent process, following one of the most violent events in nature. Similarly, around a white dwarf, especially if it's in a binary system where it can capture material, or if its own outer layers form a disk during the shedding of the planetary nebula, there could be a disk. Observations with infrared telescopes have indeed found some white dwarfs with warm dust disks, likely from disrupted asteroids. We might be catching those systems in the act of either grinding down an old planetary system or perhaps assembling a new configuration of bodies. Life's possibilities in these unlikely harbours is a subject that tickles the imagination. Around a pulsar or magnetar, it seems exceedingly unlikely for life as we know it to survive. The radiation is intense, and the environment changes are violent. But maybe in the distant future, when a pulsar's spin has slowed and its radiation weakened, if a planet remains, it could be much like a planet around a very dim, cool star, needing to huddle close for warmth. Around white dwarfs, life might have a better chance. A white dwarf, after cooling to a certain point, could provide a steady, long-lasting heat source for billions of years, though a planet would have to orbit very close to get enough warmth. There is speculation that as a white dwarf cools, it passes through a phase where it's about as luminous as a red dwarf star for a long time, meaning any planet in that narrow zone could potentially have Earth-like temperatures. However, getting a planet into that zone after the star's upheaval is the challenge. Nonetheless, some scientists have proposed looking for biomarkers, like oxygen, water, etc., in the atmospheres of planets around white dwarfs, because if such a planet exists in the right spot, it might actually be easier to detect against the small white dwarf than around a larger star. For now, we have yet to find evidence of life in such exotic locations. But just the existence of planets there widens our perspective of what a habitable world might mean. It reminds us not to be too narrow in imagining nature's possibilities. Perhaps somewhere in the galaxy, there is a rocky planet orbiting a softly glowing white dwarf, its skies illuminated by the diffuse light of 1,000 stars, since its sun is so faint, but just enough heat coming from that faint star to keep water liquid in craters warmed by geothermal heat. Or perhaps life could exist in the ocean, beneath an ice shell, on a moon, orbiting a pulsar planet, completely shielded from radiation and relying on internal tidal heat. These scenarios are speculative, certainly, but they speak to the resilience of matter and the unpredictability of cosmic evolution. In the end, the existence of these strange companions, planets around the remnants of stars, brings our exploration full circle. A star is born, it lives, it dies spectacularly, and even after death, it can have children of its own, in the form of planets, or continue to host survivors from its earlier family. The cosmos is a continuity, where endings flow into new beginnings, often in surprising ways. As we leave the realm of supernova remnants and their afterlives, we carry with us a tapestry of images, blooming nebulas from stellar shrapnel, lighthouse pulsars ticking in the dark, magnetar storms shaking space like thunder, black holes holding light captive, heavy elements being forged and flung into the void, gentle dust and molecules coalescing into new worlds, high-energy cosmic rays whispering through space, and odd, tenacious planets circling the ghosts of stars. The story of stars does not end at death. It branches out, influencing the galaxy and seeding the future. Our journey through the life and death of stars has revealed an intimate truth. We are part of this cosmic story. The atoms of our bodies were forged in stellar furnaces and distributed by supernovae. The Earth itself is a child of countless star deaths. In every breath we take, in the iron taste of blood on the tongue, in gold rings and silicon circuits, we see the handiwork of supernovae and their remnants. As we continue to explore the universe, we find that looking outward also means looking inward, understanding our own origins. And so, with the afterglow of supernovae in mind, and the quiet companionship of planets around stellar remnants, we prepare to look to the next chapter of our cosmic story, whatever it may be, knowing that the universe continually renews itself in an endless cycle of birth, death, and rebirth, all under the grand fireworks of the stars.